530 million years ago, the oceans already had monsters, but fish did not exist yet. For the first 100 million years of complex animal life on Earth, the seas were ruled by something else entirely: predators with rotating mouths, compound eyes made from thousands of lenses, bodies so alien that scientists spent decades thinking their fossils belonged to completely different animals. One of them was the largest animal on Earth for millions of years, and it was an arthropod. Another lineage grew over 8 feet long, larger than most modern sharks. Not a reptile, not a fish, a distant relative of spiders and horseshoe crabs. The first advanced eyes ever to evolve appeared in this world, and almost immediately, life on Earth began to change around them. Armor appeared, spikes appeared, creatures started burrowing into the seafloor just to avoid being seen. The pressure created by these early predators helped shape the evolution of vision, jaws, skeletons, and survival itself. And when fish finally did appear, they did not take over. For millions of years, they stayed near the bottom of the food chain, beneath creatures that had already ruled the oceans longer than dinosaurs would later rule the land. But before we continue, let me know in the comments if you have any topic suggestions you would like me to cover in future videos. By the end of this video, the ocean will look different to you, because what ruled it before fish existed was not primitive or experimental. It was sophisticated, dominant, and terrifyingly successful. Long before jaws opened in dark water, and before eyes searched across distance for movement, the planet itself was still arranging the conditions that would allow such things to exist. The creatures that would one day dominate the ancient seas did not emerge into a finished world. They inherited an ocean already ancient beyond comprehension, shaped by billions of years of slow chemical change, drifting continents, and patient microbial life. Around 600 million years ago, Earth would have been almost entirely unfamiliar from above. Most of the landmass was gathered into the southern supercontinent Gondwana, an immense aggregation of stone stretching across the lower half of the planet, while shallow tropical seas spilled across the edges of the continents in broad, luminous sheets. In many places, these waters were so clear and so shallow that sunlight reached all the way to the seafloor. The future history of the Paleozoic Ocean would unfold almost entirely within these flooded continental shelves. Warm inland seas suspended beneath an atmosphere carrying less oxygen than today, perhaps around 16%, though the amount was slowly climbing with each passing geological age. For most of Earth's history before this moment, the ocean floor belonged not to animals, but to microbes. Vast bacterial mats spread across the sediment like living fabric, flat and quiet beneath the water, harvesting sunlight and releasing oxygen molecule by molecule into the atmosphere over spans of time so enormous they resist ordinary thought. These mats built stromatolites, layered stone structures formed through countless generations of microbial growth, preserving some of the oldest visible evidence of life the planet has ever produced. For nearly 3 billion years, this world changed only gradually. There were no fast predators crossing open water, no shells cracking beneath jaws, no forests of coral or schools of fish. Life remained close to the sediment, soft and slow, moving within a biological rhythm that had endured almost unchanged since before complex animals existed at all. Then, during the Ediacaran period, something unfamiliar began to appear across the sea floor. Soft-bodied multicellular organisms emerged in shapes unlike anything dominant in the ocean today. Dickensinia rested against the sediment in flattened ribbed forms that could reach over a meter in length, resembling quilted living discs pressed gently into mud. Charnia rose upward in delicate frond-like structures anchored to the bottom, motionless beneath the currents. Sprigina crawled slowly across the seafloor in segmented forms that hinted faintly at later animal bodies without fully resembling them. These organisms existed in a world still largely absent of active predation. They were not hunters pursuing prey through water, nor prey fleeing from pursuit. Many likely absorbed nutrients directly from microbial surfaces or filtered particles drifting through the sea. The ocean remained calm in its ecological structure, with little reason for armor, speed, or complex defense. Near the boundary of the Cambrian, however, these ancient forms faded abruptly from the fossil record. Their disappearance remains uncertain even now. Some may have been outcompeted by newly emerging animals better suited to changing environments. Others may simply have been unable to survive the ecological instability spreading through the ocean floor. Beneath the sediment, small burrowing organisms had begun disturbing the seabed for the first time in Earth's history. The stable microbial mats that had covered the ocean bottom for billions of years were broken apart and overturned by tunnels, feeding traces and crawling bodies moving through the mud. Paleontologists call this transformation the Cambrian substrate revolution, though the phrase hardly captures the scale of what was happening. The seafloor itself was being reorganized into a more complex landscape filled with crevices, soft sediment, and hidden spaces. And once hiding places existed, the ancient ocean required something capable of searching for what could now disappear. The transformation did not arrive as a single moment. No wave crossed the ocean, no boundary line appeared in the water. Across roughly 20 million years, beginning around 538 million years ago, life simply accelerated with astonishing suddenness in geological terms, unfolding into forms and strategies the planet had never seen before. Paleontologists later called this interval the Cambrian Explosion, though the word explosion can feel misleading beside the slowness of stone and sediment. Even so, within that relatively brief stretch of deep time, nearly every major animal body plan known today entered the fossil record for the first time. Limbs, shells, digestive tracts, eyes, spines, segmented bodies, grasping appendages, swimming lobes, feeding structures, and armored exoskeletons appeared in overlapping succession, as though evolution had moved from whispering into rapid conversation. For billions of years before this transformation, most organisms experienced the world through chemistry and touch. The ocean was sensed through dissolved particles drifting in water, through vibration against soft tissue, through direct physical contact with nearby surfaces. Life remained intimate and local, restricted to what could be felt within immediate reach. Distance held little meaning in biological terms, because almost nothing could perceive it clearly. Then, somewhere among the early predator lineages moving through Cambrian seas, image-forming eyes emerged, not simple patches capable of detecting light and dark, but organs able to resolve shape, movement, and spatial detail across open water. For the first time in Earth's history, one animal could detect another before touching it. The consequences spread outward through the ocean with extraordinary speed. A creature visible from meters away could no longer rely on stillness alone. Bodies that had remained soft for hundreds of millions of years began hardening into mineralized armor. Spines appeared along backs and limbs. Organisms burrowed deeper into sediment or developed faster methods of movement through water. The evolutionary pressure became immediate and relentless, not through intention, but through survival itself. Paleontologist Andrew Parker later described this transition through what became known as the light switch theory, proposed in the late 1990s. Though debated in some details, The broader pattern remains striking, as increasingly sophisticated eyes appear in Cambrian fossils. Defensive structures proliferate almost simultaneously beside them, as though the ocean had entered a new sensory state from which there could be no return. Much of what is known about this ancient transition survives because of rare geological circumstances that preserved bodies usually lost to decay. In the mountains of British Columbia, the Burgess Shale holds one of the most extraordinary fossil assemblages on Earth. Discovered by Charles Walcott in the early 20th century, the site preserves not only shells and hard structures, but soft tissue, digestive systems, muscles, eye surfaces, and delicate anatomical details that normally vanish within hours after death. The animals of the Cambrian were carried from a submarine cliff into an oxygen-poor basin below, where bacterial decomposition slowed almost to stillness beneath fine sediment. Mineral replacement captured their forms in remarkable detail, allowing organisms dead for over 500 million years to remain visible within thin layers of dark stone. Across the Pacific, in Yunnan province in China, the Chengjiang fossil beds preserve another window into the same vanished ocean. Excavated extensively from the 1980s onward, Chengjiang revealed neural tissue impressions, gut contents, sensory organs, and body structures so unfamiliar that some fossils initially seemed almost impossible to classify. Together, these sites transformed scientific understanding of the Cambrian world, from scattered fragments into something almost cinematic in clarity. The ocean itself had become ecologically layered and densely inhabited. Sponge reefs rose from the seafloor in clustered formations. Burrowing animals moved constantly beneath sediment, disturbed by feeding trails and tunnels. Filter feeders extended delicate structures into passing currents, while armored arthropods crossed the bottom in slow processions. Above them moved a small number of large predators, swift and visually guided, occupying an ecological position that had scarcely existed before. At the top of this world sat one animal, and it was unlike anything that had existed before it. For nearly a century, the animal existed in pieces. Its body lay scattered through scientific literature under different names, described as separate organisms that seemed to share nothing except the same layers of Cambrian stone. One fossil appeared as a strange segmented appendage and was identified in the late 19th century as the tail of an unusual shrimp. Another, a circular arrangement of hardened plates surrounding a central opening, was classified as a jellyfish and given the name Peytoia. A flattened body preserved nearby entered the record as a worm-like creature called Lagania. No one realized they belonged together because nothing living in the modern ocean resembled the complete animal closely enough for the mind to assemble it correctly. The first fragment to receive a name became Anomalocaris canadensis, meaning abnormal shrimp from Canada, a title given in the year 1892 after the discovery of the segmented frontal appendage in the Burgess Shale. The name itself preserved the misunderstanding. Paleontologists worked carefully with what they had, but the Cambrian Ocean repeatedly violated expectations built for modern anatomy. The fossils seemed too alien, too disconnected from familiar body plans. For decades, the creature remained divided across museum drawers and scientific diagrams, waiting for someone to notice that the impossible pieces belonged to one body. That recognition finally arrived in the mid-1980s, when Harry Blackmore Whittington and his colleagues at Cambridge University re-examined Burgess Shale material in greater detail. Among the fossils was a specimen preserving the circular mouth directly attached to the body, with the grasping appendages extending forward in articulation. The realization changed Cambrian paleontology almost immediately. Three separate animals vanished overnight, and one immense predator emerged in their place, assembled at last from fragments that had spent 80 years apart. Anomalocaris moved through Cambrian water unlike anything before it. Most individuals reached roughly 1 meter in length, though fragmentary remains from related forms hint at even larger sizes, approaching 2 meters. Along both sides of its flattened body ran overlapping swimming lobes that undulated in coordinated waves, propelling the animal forward with smooth rhythmic motion. The movement has sometimes been compared to that of modern cuttlefish, though the similarity is purely functional. Anomalocaris belonged to a branch of life entirely separate from cephalopods, arriving at efficient swimming through its own evolutionary path in the warm inland seas of the Cambrian world. At the front of the head stood a pair of large stalked eyes, positioned outward on either side like suspended domes scanning the water column. Optical modeling studies published in the early 21st century revealed that each eye may have contained as many as 16,000 individual lenses. The visual resolution appears to have been remarkably advanced for its age, comparable in acuity to modern dragonflies. These were not primitive light detectors. They were sophisticated image-forming organs capable of tracking movement across distance in an ocean where many organisms still relied primarily on touch and chemical sensing. Beneath the eyes extended the frontal appendages that first entered science disguised as shrimp tails. Each appendage consisted of articulated segments lined with inward-facing spines, forming grasping limbs adapted for seizing prey and guiding it toward the mouth. That mouth remains among the strangest feeding structures in the fossil record, a rotating circular arrangement of hardened plates opening inward around a central passage. Biomechanical studies suggest it generated enough force to crush softer or lightly armored animals, though heavily mineralized trilobites may have resisted more effectively than once imagined. The evidence survives quietly in stone. Some trilobite fossils preserve circular bite marks, matching the dimensions and arrangement of the Anomalocaris mouthparts. A few of those injuries healed before death, the damaged shell regrown around the wound. Not every attack succeeded. Even in the earliest great predator of complex animal life, the hunt could fail. For millions of years, Anomalocaris occupied a category almost entirely its own, the largest known animal on Earth moving through oceans, still learning the meaning of pursuit. Yet the body plan did not end with one species alone. Around it, other relatives were already diversifying into forms stranger still, stretching the architecture of the Anomalocaridids far beyond what scientists once believed possible. The Cambrian Sea did not belong to a single ruler for long. Once the Anomalocaridid body plan appeared, evolution began shaping it into multiple forms with remarkable speed, stretching the same anatomical framework across radically different ways of life. What emerged was not one isolated predator lineage, but an entire radiation of large swimming animals occupying separate ecological roles simultaneously. For many years, paleontologists assumed such flexibility belonged mainly to later vertebrates. Yet the Anomalocaridids had already achieved it more than 500 million years ago, drifting through the early ocean in bodies that could be adapted for pursuit, scavenging, suspension feeding, and rapid visual hunting. Among the strangest was Herdia victoria, an Anomalocaridid roughly similar in size to Anomalocaris, but carrying an immense three-part frontal carapace extending outward from the head in a broad, flattened structure shaped almost like the letter H. In fossils, the carapace appears delicate and architectural, suspended above the feeding appendages like a rigid canopy moving through water. Its exact purpose remains uncertain. Some researchers propose that it stabilized the animal hydrodynamically while swimming, smoothing the flow of water across the body. Others suggest it functioned as a sensory structure, or perhaps even a display surface visible to nearby individuals in the clear Cambrian seas. Another possibility is subtler still, that the structure redirected currents toward the mouth while the animal fed. The stone preserves the anatomy with remarkable clarity, yet intention remains hidden inside silence, hundreds of millions of years old. Then came Lagania cambria, one of the discoveries that altered scientific understanding of Anomalocaris most profoundly. At first glance, its body resembled those of its relatives, broad swimming lobes rippling along the sides, while large eyes faced outward into open water. Yet the frontal appendages told an entirely different story. Instead of inward-facing grasping spines suited for capturing prey, Lagania possessed elongated delicate structures forming a mesh-like net through which water could pass while suspended particles remained trapped behind. Functionally, the arrangement resembles the filtering systems used today by basking sharks or baleen whales, organisms that move slowly through nutrient-rich water while straining plankton from the current. In the Cambrian Ocean, an anomalocarid had already evolved into a giant filter feeder, transforming the same ancestral architecture that produced active apex predators into something calm and suspension-based. The implications reshaped the lineage completely. The anomalocaridids were not specialized into one narrow ecological role. Their body plan possessed enough flexibility to generate animals occupying opposite ends of the feeding spectrum, from swift grasping hunters to drifting plankton sifters moving quietly through sunlit seas. It was less like discovering variations within a single species group, and more like uncovering an ancient evolutionary experiment broad enough to contain entirely separate modes of existence. Other members of the lineage moved in different directions again. Amplektobelia, smaller and more compact than Anomalocaris, possessed frontal appendages suggesting greater speed and maneuverability. The limbs curved inward with tighter articulation, suited perhaps for pursuing smaller and more agile prey through the water column. Its body appears built less for overpowering large armored organisms and more for rapid directional hunting in crowded Cambrian ecosystems where mobility itself had become an advantage. In the Chengjiang fossil beds of China, another relative preserved something even rarer than anatomy. Lyrapax unguispinus retained impressions of neural tissue inside the head, including enlarged frontal regions associated with visual processing. Fossilized brains are among the rarest structures in paleontology, normally lost long before mineralization begins. Yet here, in stone over 520 million years old, remained direct evidence that anomalocaridids possessed sophisticated nervous systems organized around complex sensory interpretation. These were not simple reflexive swimmers drifting mechanically through water. Their brains had already become deeply connected to sight. By then, the lineage had spread across much of the ancient world. Fossils appear in Canada, China, Greenland, Australia, Morocco, and the United States, revealing anomalocaridids as a globally distributed presence rather than an isolated regional fauna. For roughly 40 million years, they remained among the dominant large animals in the marine food chain, surviving beyond the close of the Cambrian and entering the Ordovician oceans that followed. The Cambrian ended quietly in stone. The ocean continued forward, growing denser with life, more layered, more crowded, and far larger in ecological scale than before. Evolution often appears gradual when viewed through fossil layers spread across immense spans of time, yet there are moments when the pace seems almost feverish, as though life itself has entered a period of sustained improvisation. The Cambrian oceans became one of those moments because predators had changed the mathematics of survival. Once large, visually guided hunters began crossing open water, remaining soft and undefended was no longer an efficient strategy. Every organism capable of avoiding detection, resisting attack, or escaping pursuit gained an advantage measured not in comfort but in continued existence. Predation became a shaping force powerful enough to reorganize the architecture of life itself. Before this transition, most marine animals possessed little in the way of hardened anatomy. Bodies were flexible, exposed, and biologically inexpensive to maintain. There was little reason to invest energy into mineralized armor when the surrounding ecosystem contained few threats requiring such protection. Then, within only a few million years after the Cambrian diversification began, unrelated animal lineages across the ocean independently evolved shells, spines, plates, and protective coverings built from calcium carbonate or calcium phosphate. The convergence was extraordinary in scale. Dozens of separate evolutionary branches arrived at the same solution almost simultaneously, not because they shared close ancestry, but because the surrounding environment had begun rewarding durability with relentless consistency. Among the clearest examples were the trilobites, whose bodies became living fortresses of articulated mineral armor. Their eyes alone represented one of the strangest optical experiments in Earth's history. Instead of soft lenses, like those found in most modern organisms, trilobites developed visual structures composed of calcite crystal, a transparent mineral capable of channeling light directly through rigid stone. No modern animal has repeated this solution. The lenses combined structural resilience with optical precision, allowing vision to remain protected beneath an armored exterior. Some trilobites carried hundreds of these mineral lenses arranged across sweeping crescent-shaped eyes that watched the water above, while the segmented body moved slowly across the seafloor. Many species also developed the ability to enroll completely, curling themselves into tight spheres that sealed vulnerable undersides beneath overlapping exoskeletal plates. Fossils preserve some individuals locked permanently in that defensive posture, their final movement captured before burial beneath sediment. Even in death, the behavior remains visible, a small armored body folded inward against a world that had become increasingly dangerous. Elsewhere in the Cambrian seas, entirely different anatomies emerged under the same pressure. Wiwaxia drifted across the seafloor in a slug-like form covered in overlapping scales and long defensive spines projecting upward from its back. Nothing in earlier fossil layers suggests direct ancestors carrying such structures. The armor appears to have evolved independently, assembled piece by piece in response to the changing ecological climate surrounding it. Hallucigenia sparsa moved on rigid paired spines, while soft tentacle-like limbs extended above the body, an arrangement so anatomically unfamiliar that paleontologists reconstructed the animal upside down for decades before identifying its true orientation. When its mouth was finally understood in detail, researchers discovered a ring of teeth leading inward to a tooth-lined throat, evidence that even this strange and delicate creature participated in the expanding web of predation shaping the Cambrian ecosystem. Then there was Opabinia regalis, perhaps among the most visually improbable animals ever recovered from stone. It possessed 5 eyes positioned across the head, a segmented body with lateral swimming lobes, and a flexible frontal nozzle ending in a grasping claw. When Harry Whittington presented the reconstruction publicly in the early 1970s, the audience reportedly laughed, assuming the anatomy had to be a mistake. Yet the fossils remained consistent. The Cambrian Ocean was not experimenting cautiously. It was producing body plans with startling freedom, each one tested against the pressures of survival in a rapidly escalating biological contest. Even the sediment itself recorded the shift. Fossilized burrow networks multiplied dramatically through Cambrian rock layers as more organisms abandoned exposed surfaces and disappeared into the seabed. Hiding had become a viable strategy because hunters capable of searching across distance now existed above them. The Anomalocaris did more than occupy this changing ecosystem. Their presence accelerated its transformation. Shells, eyes, spines, burrows, defensive postures, and sensory systems spread outward through the ocean in response to the selective pressure they imposed. And that chain of adaptation never truly stopped. It continued through every extinction and recovery that followed, passing quietly forward into the anatomy of nearly every complex animal alive today. Long after the great Anomalocaris disappeared from the ocean, their most common prey remained. Trilobites endured with a patience rare in the fossil record, persisting through environmental collapse, shifting continents, chemical upheaval, and the rise of entirely new predator dynasties. They are often treated as background life in illustrations of the Paleozoic seas, scattered across the sediment beneath larger creatures. Yet few animal groups in Earth's history achieved their level of evolutionary success. More than 20,000 trilobite species have been formally described, exceeding the diversity known from any other extinct animal lineage, and their fossils have been recovered from every continent on the planet, including Antarctica, where fragments still emerge from stone formed beneath oceans that vanished hundreds of millions of years ago. Their name means three lobes, referring not to the division between head, thorax, and tail, but to the long central axial ridge running down the body flanked by two plural lobes on either side. The anatomy proved remarkably adaptable. Trilobites first appeared in the early Cambrian around 521 million years ago and survived until the end of the Permian extinction approximately 252 million years ago. Their continuous existence stretched across roughly 270 million years, a span longer than the distance separating the first dinosaurs from the modern world. Vision became one of their most extraordinary specializations. Most trilobites possessed compound eyes built from calcite crystal lenses, an optical solution found nowhere else in animal history. Some species carried their eyes high on stalks, extending upward from the exoskeleton, allowing them to observe movement, while most of the body remained close to the sediment. Others developed visual surfaces wrapping around the curvature of the head, creating an almost uninterrupted field of view across the surrounding water. Deep water species occasionally abandoned sight entirely, evolving into blind forms that moved through dim environments where maintaining complex eyes no longer provided enough benefit to justify the biological cost. Among the most striking was Eglina prismatica, whose eyes grew so disproportionately large relative to the body that paleontologists have compared them to oversized goggles fixed against the head. The enlarged lenses likely gathered faint available light in deeper environments, where visibility remained limited even during daylight hours, filtering from above. The Cambrian and Ordovician seas contained not one standard trilobite form, but thousands, each adjusting the same segmented framework to different ecological pressures. Their feeding strategies became equally varied. Some species, such as the Cambrian redlichia, moved actively across the seafloor as predators, pursuing smaller organisms through shallow marine habitats. Others filtered suspended particles from passing currents. Some graze slowly across microbial surfaces much as earlier ediacaran organisms once had, while scavenging species consumed decaying organic material drifting downward through the water column. The trilobite body plan possessed a flexibility that allowed survival across multiple ecological niches simultaneously, which may explain part of the lineage's extraordinary longevity. Like all arthropods, trilobites grew by molting. Their rigid exoskeletons could not expand continuously, so they periodically shed the old shell and emerged temporarily soft beneath a newly forming one. Many fossils displayed in museums today are not preserved corpses at all, but abandoned exoskeletons left behind after successful molts. The fossil record therefore exaggerates trilobite mortality in much the same way an empty snakeskin might falsely suggest death rather than growth. In some formations, entire sea floors appear layered with discarded shells accumulated over generations of repeated molting cycles. Evidence of social behavior lingers as well. Certain species display subtle sexual dimorphism in body proportions, while mass fossil beds preserve hundreds of individuals from the same species gathered together before death. Some paleontologists interpret these accumulations as spawning events similar to those of modern horseshoe crabs, where large groups converge seasonally in shallow water to reproduce. Through all of it, trilobites survived. They endured the extinctions closing the Cambrian, persisted through the devastation at the end of the Ordovician, and passed through the late Devonian crisis that erased countless marine lineages around them. Few groups demonstrated such resilience across deep time. Only the end Permian extinction finally ended their history completely, extinguishing the last surviving branches of a lineage that had crossed nearly the entire Paleozoic world. They vanished, but the ocean floor never stopped recording them. In limestone cliffs, shale beds, desert outcrops, and mountain stone lifted from ancient seabeds, trilobites remain everywhere, pressed into rock in numbers so immense that the planet itself still seems to remember them. The close of the Cambrian did not bring quietness to the sea. Instead, life expanded outward into new layers of complexity, as though the earlier world of strange predators and armored prey had only been a beginning sketch awaiting fuller detail. Around 485 million years ago, the Ordovician period opened, and marine ecosystems entered one of the greatest diversifications Earth has ever experienced. Paleontologists call it the Great Ordovician Biodiversification Event, a long interval during which the number of marine genera roughly tripled between the beginning and end of the period. The Cambrian had introduced the major body plans of animal life, but the Ordovician transformed those raw anatomical experiments into densely interconnected ecosystems filled with specialized roles, layered food webs, and ecological relationships of increasing sophistication. Part of this expansion came from the sea itself. Global sea levels rose dramatically during the early Ordovician, flooding continental shelves across enormous regions of the planet. Vast, shallow marine habitats spread inland over low-lying continents, creating warm, nutrient-rich environments where sunlight penetrated easily through clear water. Each flooded shelf became an opportunity for diversification. More habitat produced more ecological niches, and more niches allowed organisms to separate into increasingly specialized ways of life. The ocean was no longer simply crowded with animals. It had become structurally elaborate. Reef systems illustrate the transformation clearly. In the Cambrian, sponge communities and microbial frameworks had formed relatively simple bottom structures, but Ordovician reefs rose upward into three-dimensional landscapes built by stromatoporoids and early corals. Tabulate and rugose corals spread across shallow seas in branching colonies, while sponge-like reef builders strengthened the growing frameworks beneath them. Cavities, ledges, sheltered channels, and vertical surfaces multiplied through these reef complexes, creating environments where countless organisms could feed, hide, reproduce, and compete within the same physical space. The ocean floor acquired architecture. Among the new dominant groups were the crinoids, animals sometimes called sea lilies because of their plant-like appearance despite belonging to the echinoderm lineage. Anchored to the seafloor by long, flexible stalks, crinoids extended feathery feeding arms upward into passing currents, filtering suspended particles from the water. In some regions, they formed dense colonies resembling underwater meadows, swaying continuously with the motion of the sea. Nearby lived brachiopods, shelled filter feeders superficially similar to modern clams, though entirely unrelated evolutionarily. Their hinged shells carpeted large portions of the seafloor, opening rhythmically as water passed through delicate feeding structures inside. Bryozoans joined them as colonial organisms, constructing calcium carbonate frameworks that spread outward in branching or lace-like forms across reefs and hard surfaces. Higher in the water column drifted immense populations of graptolites. Each individual organism was tiny, yet they lived as colonies linked together into elongated, floating structures, carried by ocean currents across enormous distances. Some hung vertically through the water like translucent ribbons, while others formed branching chains suspended beneath the surface. Their abundance became so immense and geographically widespread that paleontologists now use graptolite fossils to date Ordovician rock layers across multiple continents. Entire intervals of geological time can be recognized through the appearance and disappearance of specific drifting colonies. Amid this flourishing marine complexity, the first vertebrates appeared more consistently in the fossil record. These early fish-like animals remained small, jawless, and heavily armored across the head and upper body. They occupied mostly bottom-dwelling ecological roles, feeding quietly on detritus or microscopic material while larger predators moved above them. Though vertebrates had entered the oceanic story, they remained marginal participants in ecosystems still dominated by invertebrate life. Yet the scale of predation was changing once again. Above the reefs, above the drifting colonies, above the trilobite-covered sediment and forests of crinoids, a new category of hunter was emerging from the cephalopod lineage. Nautiloids began constructing long, chambered shells capable of controlling buoyancy with remarkable precision, and some species expanded their bodies to dimensions the Cambrian oceans had never approached. The Ordovician Sea had become larger in every sense, richer in species, deeper in ecological interaction, and increasingly populated by predators growing toward impossible scale within the dark water above the reefs. Some predators dominate through speed, others dominate through armor or overwhelming numbers. Cambrian ruled through scale and stillness. Suspended within the Ordovician water column, it drifted with an eerie simplicity, a straight pale shell extending through the sea like an enormous floating spike, while the living animal occupied only the open chamber at the broad front end. Based on fragmentary remains recovered from multiple continents, some individuals may have reached lengths between 6 and 9 meters, making Cambrian one of the largest predators Earth had produced up to that point in its history. In oceans already crowded with reefs, trilobites, drifting colonies, and expanding food webs, this immense cephalopod moved with a calmness that concealed extraordinary anatomical sophistication. Its shell belonged to a form called an orthocone, meaning straight cone. Unlike the tightly coiled shells associated with later nautiluses and ammonites, The Cambrian shell extended almost entirely linearly, tapering gradually toward a narrow tip trailing far behind the animal. Internally, the shell was divided into a long series of chambers separated by mineral walls. Most of these chambers contained gas, while a soft tissue tube, known as the siphuncle, passed through them from end to end. By regulating the balance between gas and liquid inside the chambers, Cambrian controlled buoyancy with remarkable precision, adjusting its vertical position in the water without constant swimming effort. The living body itself occupied only the final chamber at the wide end of the shell. From that opening, extended tentacles surrounding a hardened beak, capable of crushing shells and tearing apart prey. The beak functioned much like that of modern parrots or cephalopods, sharp and curved, designed for gripping and processing difficult food items. Everything behind the body served balance, flotation, and orientation. What appears at first glance to be an awkward burden was instead a highly specialized structure that stabilized the animal horizontally within open water. The shell acted almost like the shaft of an arrow or spear, resisting unwanted rotation while the feeding end remained poised in the correct hunting position. The scale becomes difficult to picture without comparison. A 9-meter Cambrian would approach the length of a modern city bus. If suspended indoors, the tentacles could occupy one side of a room while the shell extended outward through multiple walls beyond sight. In the Ordovician Ocean, such bodies hovered silently between reef systems and the darker open water beyond, balanced in the middle depths while smaller organisms crossed beneath them. Fossil material attributed to Cambrian has been recovered from Ordovician deposits across North America, including Ontario and Ohio, as well as Scandinavia and parts of China. The distribution suggests not an isolated regional predator, but a lineage spread across multiple ocean basins simultaneously. Wherever warm, shallow seas expanded during the Ordovician, giant orthocone cephalopods appear to have followed. Their prey reflected the growing complexity of the surrounding ecosystem. Trilobites remained among the most abundant hard-bodied animals in the sea, and likely formed a substantial portion of the diet. Early jawless vertebrates, still small and heavily armored, occupied vulnerable positions near the seafloor. Smaller cephalopods drifted through the water column, while large echinoderms moved slowly across reef structures and sediment plains. Cambrian fed across multiple trophic levels, participating in an ecosystem far more layered than the Cambrian seas that came before. Its hunting method was probably patient rather than fast. Modern nautiluses still demonstrate the same underlying strategy at much smaller scale, hovering almost motionless in dim water before lunging downward toward prey with sudden force. Cambrian likely behaved similarly, using precise buoyancy regulation to remain suspended at chosen depths, while trilobites and other organisms moved beneath it unaware. The attack itself may have been startlingly rapid after long periods of apparent stillness. Around Cambrian stretched an ocean increasingly filled with cephalopod diversity. More than 2,500 nautiloid species appeared during the Ordovician, ranging from tiny curved forms to massive straight-shelled giants, some coiled tightly, others loosely. Some occupied deep water, while others remained in shallow coastal seas. The lineage diversified into nearly every marine environment available. Above reef systems drifted sheets of graptolites, carried by currents. Below them spread crinoid forests and trilobite-covered sediment plains. Between those layers, enormous orthocones hovered in the dim water like living spears suspended upright in silence. Then, without warning from within the ocean itself, the stability of that world began to fail. There are moments in Earth's history when entire ecosystems vanish so completely that the rock record seems to pause between one world and the next. Around 444 million years ago, near the close of the Ordovician period, the ocean entered one of those intervals. The extinction that followed erased approximately 85% of all marine species, making it the second most severe biological crisis known from the history of complex life, surpassed only by the catastrophe at the end of the Permian hundreds of millions of years later. Yet despite its scale, the late Ordovician extinction remains strangely absent from public memory, buried beneath older stone and overshadowed by later extinctions involving dinosaurs and terrestrial worlds. In truth, the Ordovician Sea lost almost everything that had defined it. The collapse came in two separate pulses, divided by roughly 1 million years. Each wave struck organisms already weakened by the previous one, creating a layered extinction in which survival became temporary rather than permanent. The first phase began not within the ocean itself, but across the continents, where mountain ranges were rising along the margins of Gondwana as ancient tectonic plates collided. Newly exposed rock weathered rapidly beneath rainfall and atmospheric chemistry, drawing carbon dioxide from the atmosphere over immense spans of time. Slowly, global temperatures declined. Ice sheets expanded across the southern supercontinent, locking enormous volumes of water onto land. Sea levels fell dramatically as the glaciation intensified. Shallow continental seas that had once spread broadly across flooded shelves withdrew toward deeper basins, leaving enormous regions of marine habitat exposed or fragmented. Entire reef systems disappeared beneath falling waterlines. Warm coastal environments that had supported dense Ordovician biodiversity simply ceased to exist. For species dependent on stable, shallow seas, there was nowhere to retreat. The extinction spread not through violence, but through absence. Through the gradual removal of the environmental conditions life had adapted itself around. Then came the second pulse. As the glaciers eventually melted, sea levels rose again with destabilizing speed. Warm oxygen-poor water flooded outward across the seafloor in expanding anoxic events, suffocating benthic communities that had endured the freezing phase only to encounter a different form of collapse. The deep ocean carried little oxygen into recovering shallow habitats, and organisms dependent on stable bottom conditions disappeared beneath spreading chemical instability. What the first pulse had stranded, the second pulse drowned. The giant orthocone cephalopods suffered heavily during this transition. Cambrian and its immense relatives, once suspended through the Ordovician water column like drifting weapons, declined sharply as the ecological networks supporting them fragmented. The extraordinary diversity that had characterized the nautiloid radiation contracted into diminished remnants. Straight-shelled giants became increasingly rare, while smaller and more flexible cephalopod lineages persisted more successfully through the instability. Trilobites endured, but not unchanged. The lineage lost the majority of its families during the extinction, reducing a once overwhelming diversity into a far narrower collection of survivors. Though trilobites would continue for hundreds of millions of years beyond this point, they never again recovered the ecological dominance they possessed during the Ordovician peak. Graptolites suffered even more dramatically. From thousands of drifting colonial species spread across the global ocean, only a small fraction remained afterward, their immense curtain-like populations collapsing almost entirely from the fossil record. The descendants of the Anomalocaris also thinned further during the crisis. The great Cambrian predator lineage, already diminished from its earlier dominance, persisted only in scattered specialized forms, surviving at the edges of changing ecosystems. Much of the ancient world assembled during the Cambrian and elaborated during the Ordovician disappeared within this interval of environmental instability. Yet, some organisms endured with surprising resilience. Smaller species capable of tolerating fluctuating conditions survived more effectively than highly specialized giants. Generalists outlasted narrow specialists. Animals occupying deeper or more variable environments often survived better than those dependent on stable, shallow seas. Among the survivors were the early vertebrates, still ecologically marginal and largely confined to bottom-dwelling roles. Their very insignificance may have protected them. They required less, consumed less, and occupied niches overlooked by many larger predators. For a geological instant, the ocean grew quieter. Diversity collapsed. Reef systems faded. Ancient dynasties shrank into fragments. Then, slowly, life began assembling itself again beneath recovering seas, and the creatures rising into the emptied spaces would prove stranger still than those that had vanished before them. Recovery in deep time rarely resembles healing in the human sense. Ecosystems do not return to what they were before catastrophe. They reorganize around absence. After the end Ordovician extinction stripped away much of the marine world, the Silurian period emerged from that emptiness not as a restoration of the past, but as a quieter and more stable ocean preparing entirely new forms of dominance. Beginning around 443 million years ago and continuing for roughly 24 million years, the Silurian became one of the most consequential intervals in the history of animal life, not because it introduced sudden novelty, but because it allowed surviving lineages to expand through ecological spaces left vacant by extinction. The rebuilding happened surprisingly quickly in geological terms. Within perhaps 5 to 10 million years after the Ordovician collapse, biodiversity across the oceans was climbing once again. Sea levels rose as the Great Glacial Episode faded, flooding continental margins beneath warm, shallow water and recreating broad marine habitats across much of the planet. Chemically, the oceans stabilized. The environmental volatility that had devastated the previous ecosystems relaxed into a period of relative equilibrium, and life responded by diversifying rapidly into every available niche. Reef systems spread widely during this recovery. Built primarily by tabulate corals and stromatoporoids, the reefs of the Silurian achieved a structural complexity approaching that of modern coral systems. Layered frameworks rose upward from the seafloor in branching and mound-like formations, creating protected cavities, current channels, shaded surfaces, and feeding grounds, supporting enormous invertebrate diversity. The reef had become not simply a biological structure, but an ecosystem within an ecosystem, a vertical world crowded with movement at every scale. Across these expanding marine landscapes, older lineages recovered while new variations emerged among them. Nautiloid cephalopods diversified again after the collapse of many giant orthocones, though the Silurian seas no longer belonged solely to enormous straight-shelled hunters. Brachiopods spread densely across sediment, plains, and reef margins, opening and closing their mineral shells within steady currents. Echinoderms elaborated into increasingly varied forms, their body plans radiating outward into new ecological strategies. Recovery unfolded simultaneously at nearly every trophic level, producing ecosystems that felt mature again, layered and interconnected after the simplification that followed extinction. The vertebrates, still small and ecologically marginal, nevertheless became more diverse than at any previous point in their history. Jawless fish expanded into multiple distinct forms during the Silurian, carrying armored head shields while moving cautiously across the seafloor in search of small food particles and organic debris. Many remained close to the sediment, protected by bone yet lacking the speed or feeding mechanisms necessary for active predation. Their bodies suggest caution rather than dominance, organisms surviving within ecosystems still controlled by invertebrate hunters moving through the water above them. Yet, within the Silurian fossil record appear faint indications of something entirely new. Around 430 million years ago, the first jawed fish begin to emerge in scattered fragmentary remains. They were unimpressive creatures by later standards, small, rare, and still peripheral within marine ecosystems. Nothing in their appearance would have suggested future supremacy, but hidden within their anatomy was one of the most transformative innovations vertebrates would ever develop. The earliest jaws had arrived quietly in the margins of the Silurian Sea. At the top of that world, however, vertebrates remained secondary participants. The dominant predators of the Silurian belonged instead to the chelicerates, the arthropod lineage that today includes spiders, scorpions, and horseshoe crabs. Surviving descendants of Ordovician forms expanded dramatically during the recovery, adapting themselves to open marine hunting on a scale no arthropod had previously achieved. These were the eurypterids, often called sea scorpions, though the name barely captures their role within the ecosystem. Their bodies lengthened, their swimming appendages strengthened, and their sensory systems sharpened as they spread through coastal waters, estuaries, and shallow inland seas. The ocean that emerged after the Ordovician extinction had become warmer, more stable, and increasingly crowded once again. Yet its apex predators no longer resembled the orthocone giants drifting through the previous age. The Silurian belonged to arthropods, building themselves toward dimensions that still seem improbable, and for a span of millions of years, no animal lineage on Earth matched what the eurypterids were becoming. Long before vertebrates rose into the dominant predators of the seas, the oceans belonged to arthropods that had pushed their bodies toward dimensions almost difficult to reconcile with the word arthropod itself. Eurypterids first appeared during the Ordovician, around 467 million years ago, and endured until the catastrophe at the end of the Permian, roughly 252 million years ago. Their lineage persisted for more than 200 million years, surviving multiple extinction events while spreading across marine coastlines, estuaries, lagoons, and even inland freshwater systems. Across that immense span of time, they diversified into dozens of ecological forms, from small bottom hunters scarcely longer than a human hand to giants approaching the size of modern sharks. They are often called sea scorpions, though true scorpions had not yet evolved when the earliest eurypterids entered the water. The resemblance comes from shared ancestry. Eurypterids belong to the chelicerates, the arthropod group that would eventually include horseshoe crabs, spiders, mites, and terrestrial scorpions. Their anatomy already carried the blueprint of that lineage, expressed through segmented exoskeletons and specialized appendages arranged around a broad frontal body section called the prosoma. Behind it extended the opisthosoma, tapering gradually into a tail spine known as the telson, which in some species may have aided steering or stabilization as they moved through the water. The front section bore 6 pairs of appendages. The first 4 pairs functioned in walking, handling prey, and manipulating food toward the mouth. In many species, the 5th pair evolved into broad paddle-like limbs capable of generating strong swimming strokes through the water column. The 6th pair varied dramatically depending on ecological role. Some species carried enlarged grasping claws, Others possessed additional paddles or specialized limbs, suited for probing sediment and seizing struggling prey. Their bodies reveal a lineage experimenting continuously with different forms of predation. The eyes of eurypterids rested high on the prosoma, positioned to detect movement in the water above and around them. Most species possessed two large compound eyes, supplemented by smaller, forward-facing ocelli. Their visual arrangement suggests predators adapted for tracking silhouettes and motion through dim aquatic environments, watching the world while remaining difficult to detect themselves beneath suspended sediment or dark water. Even the placement of the eyes contributes to the impression of an animal designed for stealth and sudden acceleration. Their sizes ranged enormously. Some eurypterids remained modest creatures barely 10 centimeters long, inhabiting shallow coastal habitats or river systems. Others expanded into dimensions unmatched by any arthropod alive today. The largest known species, Dunkleosteus renaniae, is estimated to have reached around 2.5 meters in length. That estimate comes from a fossilized claw fragment discovered within the Prüm Formation of Germany, dating to the early Devonian around 390 million years ago. The claw alone measured roughly 46 centimeters long, nearly the size of a human forearm. One isolated appendage, preserved in stone for hundreds of millions of years, hints at an animal large enough to dominate entire aquatic systems. Another giant, Pterygotus anglicus, approached 1.5 meters in length and is known for more complete fossil material recovered across North America, Europe, and Australia. Its forward-facing chelicerae formed powerful grasping claws capable of seizing armored prey, while its paddle limbs generated steady propulsion through open water. These were not slow-moving crawlers confined to the sediment. Their swimming mechanics indicate active cruising predators, capable of sustained movement through the water column, pursuing prey rather than merely waiting for it to approach. Their ecological versatility was extraordinary. Some eurypterid species remained fully marine throughout their lives, inhabiting coastal seas and reef systems. Others tolerated brackish estuaries or freshwater rivers far inland. In doing so, eurypterids became the first truly large predators to colonize inland aquatic environments, extending arthropod dominance beyond the open ocean and into waterways that no giant hunter had previously occupied. Wherever they spread, they entered ecosystems already crowded with armored fish, trilobites, cephalopods, and countless invertebrate lineages rebuilding after earlier extinctions. The Silurian seas had become dense with life again, and eurypterids moved through that abundance as apex hunters whose prey included nearly every large animal sharing their waters. Across the Silurian seas, life no longer arranged itself in simple layers of hunter and hunted. The water had become crowded with competing appetites, overlapping territories, and predators capable of preying upon one another as readily as they consumed smaller animals below them. Reef systems stretched across shallow continental shelves, dense with suspended particles drifting through warm currents, while above and between those reefs moved an increasingly complicated web of armored bodies, grasping limbs, and searching eyes. At the highest level of this living structure swam the great eurypterids. Pterygotus and Dunkleosteus crossed estuaries and coastal waters with the confidence of animals facing little resistance from anything larger than themselves. Their paddle limbs pushed them through the water in long measured strokes, while their forward appendages searched for movement beneath them. Large jawless fish formed part of their diet, especially slower, bottom-feeding species, unable to accelerate quickly away from attack. Smaller eurypterids were also hunted, as were large nautiloids drifting too close to the shallows. Trilobites, armored worms, and shelled invertebrates disappeared into their grasping claws whenever opportunity allowed. Nothing substantial in the Silurian Sea existed entirely outside the reach of these hunters. Beneath them moved a second tier of predators and opportunists. Medium-sized eurypterids occupied coastal lagoons and reef margins, feeding on juvenile fish, smaller arthropods, and soft-bodied invertebrates hidden among coral frameworks. Recovering nautiloid cephalopods, diminished from the colossal scale achieved in the Ordovician, yet still formidable, drifted through deeper channels and shadowed reef edges. Their tentacles explored the water constantly, searching for trilobites or fish vulnerable enough to seize. Along sheltered shorelines, large sea scorpions competed with some of the earliest primitive jawed fish, whose appearance remained modest and almost unnoticed against the dominance of arthropods and cephalopods surrounding them. Farther down the food web lived the agnathans, the jawless armored fish that spent much of their lives close to the sediment. Hemicyclaspis moved slowly over the seafloor with a flattened body and broad head shield shaped almost like a curved shovel. Cephalaspis possessed wing-like extensions around the head, allowing it to stabilize itself near the bottom while searching for edible particles drifting through the current. Pteraspes carried a more streamlined form, perhaps capable of slightly faster movement through open water. None of them were apex predators. They fed on detritus, microbial material, and tiny invertebrates buried within the sediment. Yet their anatomy already reflected the immense pressure imposed by the hunters above them. Their bony head shields were not merely armor. Embedded throughout those shields were sensory pore systems capable of detecting changes in water pressure and faint electrical disturbances nearby. In the dim conditions of coastal Silurian waters, those sensory fields acted like invisible warning systems, allowing the fish to perceive movement before direct contact occurred. The bodies of these early vertebrates were becoming instruments tuned specifically for survival beneath eurypterid predation. Below the agnathans remained the dense and persistent communities that supported the entire ecosystem. Trilobites still crossed the sediment in enormous numbers despite their long decline from earlier Ordovician abundance. Brachiopods anchored themselves to reef surfaces, filtering suspended nutrients from the water. Crinoids extended feathery arms into passing currents, while worms tunneled through soft mud beneath them. Small mollusks crept between reef crevices and shell beds, feeding quietly within the immense machinery of the ocean floor. The violence within this ecosystem did not move in neat directions. Fossilized eurypterid remains, bearing bite marks from larger eurypterids, reveal that predator often became prey within the same lineage. Competition intensified wherever food resources narrowed or territories overlapped. Some jawless fish fossils preserve healed injuries along their armored heads and bodies, wounds consistent with failed arthropod attacks. Bone regrew around the damaged regions, evidence that at least some individuals escaped alive after encounters in the water above them. Even the largest eurypterids carried moments of profound vulnerability. Like all arthropods, they periodically shed their exoskeletons as they grew. During the hours following molting, their new outer covering remained soft and fragile. Fossilized molts, preserved within sheltered, fine-grained sediments, suggest these animals withdrew into protected environments while waiting for their armor to harden again. In those intervals, an apex predator could become defenseless prey. The Silurian Ocean was not a stable ladder of dominance. It was a shifting negotiation between hunters sharing the same water, each adapting against the pressure imposed by the others. Along the edges of that negotiation, small-jawed vertebrates continued refining an anatomical innovation that would eventually transform the entire structure of the sea. The transformation began quietly, deep inside the throat of small fish that still spent most of their lives near the sediment, avoiding the larger hunters that moved above them through the Silurian water. Nothing about those early vertebrates suggested dominance. Their bodies remained modest, their movements cautious, their role within the ecosystem still marginal. Yet within their anatomy, an older structure had begun changing shape for reasons entirely unrelated to feeding, and that slow alteration would eventually reorganize the entire ocean. In jawless fish, the throat was supported by a series of arches made from cartilage or primitive bone. These gill arches held the breathing chamber open while water passed across the delicate respiratory surfaces inside. They functioned as structural supports, not as tools for capturing prey. Food entered the mouth largely through suction, with the animal drawing small particles or soft-bodied organisms inward as water flowed across the gills. This method worked adequately in a world dominated by detritus, microorganisms, and fragile prey. It offered little advantage against larger, armored, or fast-moving animals. Over millions of years, the foremost pair of those gill arches began to shift position. They rotated outward slightly and developed the ability to hinge against themselves. A support structure meant for breathing slowly acquired a second function. Instead of merely holding tissue open, it could now close with controlled force. The first jaws were not invented in a sudden leap. They emerged through gradual modification, the patient reshaping of an older anatomy under the pressure of survival in increasingly competitive seas. That transition survives in the fossil record with extraordinary clarity. In China, paleontologists uncovered a placoderm fish called Entelognathus primordialis, dating to roughly 419 million years ago. Its skull preserves a remarkable arrangement of bones linking the jaw structures of later vertebrates directly to the gill arches of earlier jawless ancestors. The connection appears almost like a sentence, interrupted midway through its transformation, with older anatomy and newer anatomy existing simultaneously in the same animal. Stone preserved the moment when one biological system began becoming another. The consequences of jaws reached far beyond the mouth itself. Suction feeding restricted animals to prey that was small, soft, or slow enough to drift inward with passing water. Jaws changed the scale entirely. With jaws came the ability to seize, crush, cut, and process hard-bodied organisms. Armored prey that once existed beyond reach suddenly became available as food. Fast-moving animals could be gripped rather than merely inhaled. The ocean's available energy expanded dramatically for any lineage capable of exploiting it. At nearly the same time, early jawed fish evolved paired fins positioned along both the front and rear portions of the body. Jawless fish lacked the ability to maneuver precisely through three-dimensional space. Their movement remained comparatively limited, dependent largely on simple lateral motion through the water. Paired fins transformed balance and control. Fish could bank through turns, accelerate upward, reverse direction, or hold position against changing currents with far greater precision. Hunting itself became a more dynamic act, dependent not only on sensing prey but actively pursuing it. Almost immediately after jawed vertebrates appeared, they separated into two major evolutionary paths. One lineage, the chondrichthyes, developed skeletons composed primarily of cartilage and would eventually give rise to sharks and rays. The other, the osteichthyes, developed bony internal skeletons and became the ancestors of nearly every other vertebrate lineage to follow, including ray-finned fish, lobe-finned fish, amphibians, reptiles, birds, mammals, and humans. Within those two branches lay the future architecture of vertebrate life for hundreds of millions of years afterward. Evidence suggests that proto-sharks already existed during the height of eurypterid dominance. Tiny shark denticles, scales formed from the same tissue as teeth, appear in Ordovician rocks, dating back around 450 million years. While giant arthropods ruled the open water, small cartilaginous fish already moved beneath them, surviving quietly in the margins of the ecosystem. During the Silurian, those early jawed fish remained minor figures within a world still dominated by eurypterids and cephalopods. Their bodies were small, their ecological role uncertain, their presence easy to overlook beside the giants surrounding them. Yet the essential structure had already formed. Bone, cartilage, fins, and jaws were assembling themselves into a design that would soon move from the edge of the food web to its center. By the opening of the Devonian, the balance of the ancient ocean had begun to tilt. The change did not arrive as a sudden collapse of the older rulers, but as a slow transfer of momentum from one lineage to another. For tens of millions of years, vertebrates had survived in the margins beneath arthropods and cephalopods that dominated the upper tiers of marine life. Now, between roughly 419 and 359 million years ago, fish expanded outward into the sea with a scale and diversity the planet had never seen before. 19th century geologists later named this interval the Age of Fishes after encountering Devonian rock layers crowded with fossil remains. Entire stone formations seemed packed with jaws, armor plates, scales, fin spines, and skulls preserved in extraordinary detail. The variety alone altered scientific understanding of vertebrate history. Fish were no longer peripheral creatures lingering at the edges of the ecosystem. In the Devonian, they became architects of the ocean itself. The seas they inherited were broad, warm, and flooded across continental shelves under high global sea levels. Reef systems expanded to dimensions unmatched anywhere else in the Paleozoic world. Stromatoporoid sponges and rugose corals constructed immense underwater frameworks, stretching for hundreds of kilometers, forming dense labyrinths of channels, caverns, and vertical walls. In some regions, these reef systems rivaled the geographic scale of the modern Great Barrier Reef. Countless smaller organisms lived within them, feeding, hiding, reproducing, and drifting through the filtered sunlight, moving down from above. Within this expanding environment, 4 major vertebrate groups spread through nearly every ecological niche available. Placoderms, the armored-jawed fish, emerged first as some of the most visually imposing animals of the period. Their heads and thoraxes were encased in thick, interlocking bony plates, giving them the appearance of living siege engines moving through the water. Alongside them swam the Chondrichthyes, the cartilaginous fish lineage that would eventually produce sharks and rays. Sarcopterygians, the lobe-finned fish whose muscular fins already contained the deep anatomical blueprint of future limbs, moved through coastal habitats and deeper channels alike. The actinopterygians, or ray-finned fish, diversified quietly but persistently, laying the foundation for the overwhelming majority of modern fish species that would appear far later. Among all these groups, the placoderms possessed perhaps the most unusual feeding mechanism the ocean had yet produced. Most vertebrates opened the mouth primarily by lowering the lower jaw. Placoderms transformed the entire front of the skull into part of the feeding apparatus. As the lower jaw dropped downward, the armored head simultaneously tilted upward, creating an enormous gape in a fraction of a second. The movement resembled a trap door, unfolding in 2 directions at once. This mechanism provided two enormous advantages. First, it allowed much larger prey to pass into the mouth opening without requiring a proportionally larger skull. Second, the rapid expansion generated powerful suction forces in the surrounding water. Before physical contact even occurred, nearby prey could be pulled inward by the pressure change created as the mouth opened. In crowded reef systems where maneuverability and rapid strikes determined survival, that feeding strategy became extraordinarily effective. Placoderms diversified rapidly across the early Devonian seas. Some remained small bottom feeders probing sediment for invertebrates. Others expanded into open water as fast-moving predators capable of consuming large armored prey. Hundreds of species appeared within a relatively short geological span, occupying ecological positions once dominated by older lineages. The eurypterids did not disappear immediately. Large forms still survived, including Dunkleosteus in the early Devonian, and some continued ruling estuaries and freshwater systems. Yet their dominance in open marine environments steadily weakened as jawed fish expanded into waters previously controlled by arthropods and nautiloids. The struggle unfolding across the Devonian Ocean became one of the clearest ecological transitions preserved anywhere in the fossil record. Two entirely different evolutionary strategies, external armor and jointed limbs on one side, internal skeletons and jaws on the other, competed for the same apex predator roles beneath the warm surface of the sea. By the Middle Devonian, the outcome of that contest had become increasingly clear. One placoderm, in particular, rose above the others, carrying the full power of the new vertebrate architecture into the center of the oceanic food web. Its name was Dunkleosteus. In the Middle Devonian seas, there were predators larger than sharks, heavier than eurypterids, and built with a kind of mechanical violence unlike anything the ocean had produced before. Dunkleosteus torelli moved through those waters as the definitive apex hunter of its age, a vertebrate whose arrival marked the permanent transfer of marine dominance toward fish. Earlier predators had ruled through claws, segmented armor, and external skeletons. Dunkleosteus carried its power internally, through jaws and muscle and articulated bone, the architecture of a new world beginning to assert itself over the old one. The animal was named after David Dunkel, the paleontologist at the Cleveland Museum of Natural History, who spent decades studying fossils from the Cleveland Shale, the dark Devonian rock formation where the most complete remains were uncovered. Even now, most reconstructions of Dunkleosteus are built from partial skeletons because cartilage and softer tissues rarely survived fossilization. The massive armored head, however, endured with extraordinary clarity, preserving the defining features of the animal in heavy stone. Its full body length has remained the subject of continuing revision. Earlier reconstructions proposed animals approaching 10 meters long, while more recent comparative studies, published in 2024, suggest most individuals likely measured between roughly 4.5 and 5.5 meters, with unusually large specimens potentially exceeding that range. Even at the lower end of those estimates, Dunkleosteus rivaled the size of a large great white shark, though its proportions were entirely different. The front quarter of the body formed an immense armored structure dominated by interlocking bony plates surrounding the skull and thorax. The head shield alone exceeded 60 centimeters in some specimens. Bone overlapped bone in articulated joints designed not merely for protection but for force transmission. The skull resembled a mobile battering ram suspended at the front of a fast-moving animal. Unlike later sharks, Dunkleosteus possessed no true teeth. Instead, the jaw bones themselves evolved into sharpened cutting blades. As the upper and lower edges scraped against one another during feeding, they continuously maintained a keen cutting surface through wear, eliminating the need for replacement teeth entirely. Biomechanical analysis has revealed just how devastating that system became. A study published in Biology Letters during 2006 modeled the bite mechanics of Dunkleosteus and estimated jaw tip forces around 4,400 newtons, with concentrated blade contact forces approaching 5,300 newtons. Among fish, only a handful of modern species approach similar values. Combined with its reinforced skull, those forces allowed Dunkleosteus to process heavily armored prey that earlier vertebrates could scarcely damage. Yet raw force alone does not fully explain its success. The placoderm feeding mechanism reached its most refined form in this animal. As the lower jaw dropped, the entire armored skull tilted upward simultaneously, opening the mouth in roughly 20 milliseconds. The speed of that movement generated intense suction forces in the surrounding water. Prey could be drawn inward before the cutting blades even touched them, making escape extremely difficult once the strike began. The Cleveland Shale preserves traces of its feeding behavior in remarkable detail. Fossilized pellets of compressed bone fragments have been discovered near Dunkleosteus remains, evidence that the fish swallowed prey in large sections before regurgitating indigestible material, behavior closely resembling that of modern sharks and predatory birds. One specimen even preserves partial remains of smaller fish within the body cavity itself. Direct fossil evidence of diet frozen in stone across hundreds of millions of years. Dunkleosteus was not confined to a single sea. Related fossils and equivalent formations appear across Ohio, Morocco, Belgium, Poland, and China, indicating a predator distributed through multiple Devonian ocean basins simultaneously. It shared those waters with large sharks, other placoderms, lobe-finned fish, ray-finned fish, and the final giant eurypterids lingering along coastlines and estuaries. Never before had vertebrate apex predators diversified so broadly within the same marine world. For a geological moment, the Devonian Ocean achieved a kind of unstable abundance, crowded with enormous hunters competing through radically different body plans. Dunkleosteus stood at the center of that world, not merely as another predator, but as evidence that fish had inherited the role once held by arthropods and cephalopods. And then, as the planet had done before, the world began changing again. Long before sharks became symbols of streamlined perfection, they experimented with forms that seemed almost improvised, as though evolution itself was testing possibilities faster than ecosystems could stabilize around them. In the Devonian seas, while placoderms held the dominant predator role, early sharks were diversifying quietly through side channels of anatomy and behavior, producing body plans so unusual that modern oceans preserve only faint echoes of their creativity. These were not yet the rulers of the marine world. They were prototypes, exploring solutions that no later lineage would fully repeat. Among the most familiar of these early forms was Cladosalash, a shark known primarily from the Cleveland Shale, the same dark deposits that preserved Dunkleosteus. The two animals shared the same waters, though not the same ecological authority. Cladosalash reached lengths approaching 1 8/10 meters and possessed a body already recognizable as distinctly shark-like, with a narrow profile, flexible tail, and efficient cruising form. Its forked tail generated sustained forward propulsion suited for long-distance movement through open water, an indication that active pursuit predation was already becoming central to shark ecology. Yet its anatomy retained peculiar absences. Unlike most later sharks, Cladoslate lacked heavily calcified scales across much of the body. Its skin was smoother, lighter, almost unfinished by comparison with the dense dermal armor of future species. Fossil specimens preserving stomach contents reveal partially swallowed fish arranged tail first within the digestive tract, suggesting rapid attacks from behind in which prey was seized during pursuit and consumed head last as momentum carried predator and victim forward together through the water column. Elsewhere in the Devonian and early Carboniferous seas, other sharks departed even further from familiar forms. Stethecanthus was a comparatively small predator, but its appearance bordered on surreal. Rising from its back was a flattened dorsal structure covered in enlarged denticles resembling a brush of tiny teeth. A matching patch occupied the top of the head. When lowered together, these surfaces meshed in a way unlike any modern shark anatomy. Paleontologists have proposed that the structure functioned either as a mating clasp, a species recognition display, or perhaps a signal used during territorial interactions. Whatever its purpose, the animal carried a biological architecture that later sharks abandoned entirely. Then came falcatus, appearing shortly after the Devonian in the Carboniferous, but emerging directly from the same experimental lineage. Some fossil slabs preserve pairs of individuals facing one another, locked in positions that resemble intimate behavioral interaction, frozen without warning beneath ancient sediment. The male possessed a long, curved spine projecting forward over the head like an ornamental blade, while the female lacked the structure entirely. These paired fossils are interpreted as the oldest preserved vertebrate courtship behavior known in the fossil record, a private biological moment surviving across hundreds of millions of years through improbable geological stillness. Beneath these strange outward forms was a material innovation that would ultimately outlast armored fish, giant arthropods, and countless marine dynasties. Shark skeletons were built primarily from cartilage rather than dense bone. That condition is often mistaken for primitiveness, though it offered profound advantages. Cartilage was lighter, more flexible, and capable of shaping continuous curves, difficult to achieve with rigid bone. It also permitted ongoing skeletal growth throughout life, allowing the body to adapt dynamically as the animal matured. Their reproductive biology was equally advanced. Fossils from the Devonian onward preserve claspers in males, evidence of internal fertilization. Unlike the external spawning strategies common among many bony fish, sharks invested directly in fewer offspring with greater developmental protection. It was a slower strategy, but a more resilient one during ecological instability. That resilience mattered more than dominance. During the Devonian, sharks were not yet the uncontested rulers of the sea. Dunkleosteus and the great placoderms occupied that position. But while armored giants specialized toward immense force and ecological supremacy, sharks accumulated versatility instead. Flexible skeletons, efficient locomotion, durable sensory systems, and sophisticated reproduction formed a toolkit capable of surviving environmental collapse. When later extinctions stripped oceans down to scattered survivors, those experiments endured. The strange sharks of the Devonian vanished one by one, but the underlying design continued forward through every catastrophe that followed. The first forests did not arrive with noise. They spread slowly across the Devonian continents in dense, wet silence, their roots pressing into bare stone that had once stood untouched beneath empty skies. Primitive vascular plants, followed by taller tree-like forms such as Archaeopteris, extended networks of roots deep into the ground, breaking apart rock surfaces that for billions of years had weathered only through wind and rain. Rivers carried the loosened minerals toward the sea in quantities the planet had never processed before, and the oceans responded with a chain reaction that unfolded across millions of years. Around 375 million years ago, the late Devonian extinction began. Unlike earlier extinction events that struck in relatively abrupt geological moments, this crisis unfolded in waves, interruptions, and recoveries that repeatedly collapsed back into catastrophe. Across approximately 25 million years, ecosystems rebuilt themselves only to fail again, as though the ocean had entered a prolonged state of instability from which it could not fully emerge. The first major pulses are known as the Kellwasser events, occurring between roughly 375 and 372 million years ago. Their origins appear closely tied to the expansion of land plants and the emergence of the first true forests. As roots fractured continental rock, enormous quantities of phosphorus and nitrogen washed downstream into shallow coastal seas. Nutrients that once entered marine systems gradually were now arriving in surges. Phytoplankton populations exploded across continental shelves in blooms of extraordinary scale. When these vast blooms died, their decomposition consumed dissolved oxygen from the surrounding water. Anoxia spread outward through shallow marine environments like an invisible tide. Bottom waters lost the oxygen necessary to sustain complex animal communities, and entire ecosystems began collapsing from beneath. Reef systems that had dominated Devonian oceans for tens of millions of years suffered especially severe losses. The great stromatoporoid and coral reef networks, among the largest reef ecosystems of the Paleozoic, declined catastrophically during the Kellwasser intervals. After their collapse, reefs would not return to comparable ecological prominence for approximately 100 million years, creating the longest reef gap in Earth's history. The effects reached upward through every trophic level. Dunkleosteus and the placoderms, rulers of the Devonian seas for nearly 70 million years, disappeared entirely by the end of the extinction sequence. No placoderm lineage survived beyond the close of the Devonian. Their armored skulls, once symbols of unmatched dominance, vanished from the ocean permanently. The great eurypterid predators declined as well. The lineage that had once produced Dunkleosteus no longer generated giant marine hunters. A few smaller eurypterids endured in brackish or freshwater environments, but their age of scale and dominance was over. For a time, partial recovery emerged between extinction pulses. Marine ecosystems stabilized unevenly, species diversified into abandoned niches, and food webs regained temporary complexity. Then came the Hangenberg event, around 359 million years ago, the final blow in the late Devonian crisis. Rapid climatic cooling altered circulation patterns across the ocean, while renewed anoxia spread through marine habitats already weakened by millions of years of ecological disruption. Large vertebrate lineages collapsed in succession. Survivors became fewer, smaller, and increasingly generalized. Yet within those survivors lay the architecture of the future. Sharks endured, ray-finned fish endured, lobe-finned fish endured. The earliest tetrapods, vertebrates that had already begun moving between water and land during the Devonian, endured as well. These were not necessarily the dominant animals before the crisis. Many occupied ecological margins, surviving through flexibility rather than supremacy. Their bodies demanded less specialization. Their feeding strategies tolerated instability. Their reproduction and physiology adapted more easily to changing environments. When the extinction pulses finally subsided and marine ecosystems began assembling themselves once more, the upper layers of the oceanic food web stood almost empty. The armored dynasties of the Devonian were gone, the giant arthropods diminished, the reefs shattered. Into that silence moved the survivors that had waited for opportunity rather than control, and from them the foundations of the modern ocean slowly began to rise. By the opening of the Carboniferous, the oceans had entered another long recovery, though this time the rebuilding carried a different character. The armored rulers of the Devonian were gone, the giant placoderms erased so completely that only fragments of bone remained sealed inside dark shale. Into the empty spaces moved sharks and ray-finned fish, diversifying with extraordinary speed across nearly every marine environment available to them. What followed was not merely an increase in species count, but an eruption of anatomical experimentation unlike anything earlier vertebrates had attempted. The Carboniferous period, stretching from roughly 359 to 299 million years ago, is often remembered for vast coal forests spreading across humid continents. Yet beneath those fern canopies and swamp skies, the seas were becoming stranger than the land itself. Paleontologists sometimes describe this interval as the golden age of shark evolution because of the sheer diversity that emerged within it. Dozens of shark families appeared, many bearing forms with no equivalent in modern oceans. Evolution seemed unconcerned with familiarity. It explored structure freely, shaping predators whose bodies now appear almost impossible. Among the most remarkable was Helicoprion besinoe, an animal related not to true sharks but to chimeras, distant cousins within the same cartilaginous lineage. Its most famous feature was a spiral-toothed whorl embedded within the lower jaw, a continuously growing coil of serrated teeth unlike any feeding structure known before or since. As new teeth formed at the front, older teeth rotated inward toward the center of the spiral, preserving the entire growth history of the jaw in a single tightening curve. Some whorls reached diameters approaching 45 centimeters, large enough to dominate the lower face of the animal. For more than a century after the first discovery in 1899, scientists could not determine where the structure belonged. Isolated whorls appeared so bizarre that serious anatomical reconstructions placed them along the dorsal fin, attached to the tail, or even projecting outward from the snout. Only in 2013, through computed tomography scans of associated skull material, did researchers finally confirm that the entire structure sat within the lower jaw. There it functioned as a rotating slicing mechanism, likely specialized for cutting soft-bodied cephalopods into manageable pieces. The motion resembled a continuously renewing circular blade hidden inside the mouth. Another Carboniferous predator, Edestus giganteus, pursued an equally strange solution to feeding. Its teeth were arranged not in replaceable rows like those of modern sharks, but in single advancing lines extending from both upper and lower jaws. New teeth pushed older ones forward rather than replacing them, until enormous blade-like projections extended well beyond the mouth itself. Because the jaws could not fully close, the animal likely fed through upward and downward slicing motions, cutting prey with paired scissor-like arcs rather than crushing or tearing. Smaller species experimented as well. Bandringa possessed an elongated rostrum reaching nearly half its total body length, creating a body profile unlike any later shark. Fossils occur in both marine and freshwater deposits, indicating that this species migrated between environments, perhaps entering freshwater systems for reproduction in a pattern faintly resembling later salmon or bull sharks. Whether it hunted actively or filtered prey from sediment remains debated, but its anatomy suggests a level of ecological specialization already becoming sophisticated during the Carboniferous. Alongside these cartilaginous experiments moved the coelacanths, lobe-finned fish, whose lineage had first appeared earlier in the Devonian. In Carboniferous seas, they diversified quietly among reefs and deeper coastal waters, occupying stable ecological positions while more dramatic predators transformed around them. Their importance would not become fully apparent until far later, though even now their persistence hinted at an unusual resilience within the marine world. The Carboniferous Ocean was not a crude preliminary stage waiting for modern ecosystems to emerge. It was complete within itself, filled with structures, predators, and evolutionary solutions that belonged entirely to its own age. Spiral jaws turned through dark water beneath reef shadows. Blade-toothed hunters crossed shallow inland seas. Forest rivers drained into coastal lagoons, crowded with animals unlike anything alive today. The sea had become an alien realm, built from experiments that would never be repeated in quite the same way again. By the beginning of the Permian, the ancient dynasties of the Paleozoic had already survived more catastrophe than most lineages in Earth's history would ever encounter. Oceans had frozen and suffocated, reefs had risen and vanished, and predator lineages that once appeared invincible had collapsed into scattered remnants. Yet life persisted through adaptation, retreat, and endurance. The Permian period, extending from roughly 299 to 252 million years ago, became the final long chapter of that old world, a closing age where survivors from the Cambrian still drifted through waters, already preparing for something entirely different. The continents had assembled into the immense supercontinent Pangaea, a single connected landmass stretching across much of the planet. Surrounding it lay Panthalassa, an enormous global ocean extending beyond every horizon, while the shallower Tethys Sea curved inward along tropical coastlines and continental shelves. Ocean circulation patterns shifted beneath this planetary arrangement. Vast interior deserts formed on land, while coastal seas remained warm and productive, supporting ecosystems that had slowly rebuilt themselves from the ruins of earlier extinctions. Yet beneath that apparent stability, many ancient groups had already entered decline. Trilobites, once among the most successful animals in Earth's history, persisted only as scattered survivors. Across 270 million years, they had diversified into more than 20,000 known species, adapting to nearly every marine environment imaginable. Now, only a few families remained, restricted to narrow ecological spaces where competition and environmental pressure had not yet erased them completely. Their compound calcite eyes still scanned the seafloor, their segmented bodies still crossed marine sediment, but the vast trilobite empire that once dominated Paleozoic oceans had contracted to a final, fragile thread. The eurypterids had retreated even further. Their great marine forms were gone, no longer producing the giant swimming predators that once ruled Silurian waters. By the Permian, surviving eurypterids occupied freshwater rivers, estuaries, and brackish lagoons, smaller in size and ecologically marginal compared with their ancestors. They endured quietly at the edges of the world that had replaced them. Fossils from approximately 252 million years ago represent the last known traces of the entire lineage, ending a history that stretched back more than 200 million years. Meanwhile, the oceans themselves continued changing shape beneath new evolutionary pressures. Sharks diversified aggressively through Permian seas, producing forms that still carried the anatomical experimentation of the Carboniferous. Helicoprion persisted with its spiral tooth whorl, while Edestus and related predators extended blade-like dental structures through open water. Cartilaginous fish occupied apex roles once dominated by placoderms, and unlike many earlier predator groups, sharks retained a flexibility that allowed them to move between ecological positions rather than depend on a single, specialized strategy. Near the close of the Permian, additional predator lineages began appearing along coastal margins and shallow marine environments. Early marine reptiles, still primitive compared with later Mesozoic giants, entered the oceans in tentative forms. Their rise remained only beginning, but it signaled that vertebrate evolution was preparing to reorganize marine ecosystems yet again. Ray-finned fish diversified steadily as well, expanding through reefs, coastal shallows, and open water with increasing ecological confidence. For a time, the Permian Ocean achieved something resembling equilibrium. Ecosystems stabilized across Panthalassa and the Tethys. Food webs layered themselves into durable structures shaped by hundreds of millions of years of accumulated evolutionary pressure. Survivors from the Cambrian, Ordovician, and Devonian extinctions occupied the same world simultaneously, their histories overlapping in one immense marine tapestry built from repeated collapse and recovery. Then, around 252 million years ago, the balance failed more completely than at any previous point in Earth's history. The end Permian extinction eliminated approximately 96% of all marine species. The last trilobites disappeared forever. The last eurypterids vanished beside them. Most shark lineages died as well, along with reefs, ammonoids, and countless other marine groups. When the oceans recovered afterward, they no longer resembled the Paleozoic seas that had existed since the Cambrian. For the first time, the foundations of the modern marine world began to emerge from the silence left behind. Not every lineage vanished beneath the weight of extinction. Across the hundreds of millions of years that carried the oceans from the Cambrian into the modern world, a small number of ancient body plans endured through every collapse, crossing intervals that erased entire dynasties around them. Their survival was rarely tied to dominance. Most were not the largest predators, nor the fastest swimmers, nor the most specialized hunters of their age. They persisted because their biology allowed flexibility when ecosystems failed, and because they occupied corners of the ocean that catastrophe could not fully reach. Sharks became the clearest example of this resilience. From the Ordovician onward, they survived every major extinction event that transformed Paleozoic seas. Entire reef systems disappeared, oxygen collapsed across shallow oceans, and predator hierarchies dissolved repeatedly. Yet shark lineages endured through all of it. Their success appears rooted in adaptability rather than perfection. Different species could feed on plankton, fish, carrion, mollusks, or large vertebrates, depending on ecological conditions. Some matured rapidly and reproduced before environmental shifts could erase populations entirely. Others occupied deeper waters, where extinction pressures tied to shallow marine collapse were less severe. Their cartilaginous skeletons also preserve poorly compared with bone, meaning the fossil record almost certainly underestimates the true scale of shark diversity across ancient oceans. The nautiluses carried forward another inheritance from the deep Paleozoic. Modern nautiluses are the coiled descendants of the orthocone cephalopods that once filled Ordovician seas with hovering living spears. Their lineage declined from thousands of species to only 6 surviving forms today, yet the underlying architecture remained astonishingly stable. Gas-filled chambers still regulate buoyancy through the siphuncle, allowing precise movement through the water column, much as their ancestors controlled depth hundreds of millions of years ago. Tentacles still extend from beneath the shell, opening in slow, deliberate motions, preserving a body plan older than vertebrate dominance itself. The coelacanths carried an even stranger continuity. Lobe-finned fish first appeared during the Devonian, but by the late 20th century, scientists believed coelacanths had vanished 65 million years earlier alongside the non-avian dinosaurs. Then, in 1938, a living specimen was recovered off the coast of South Africa. Named Latimeria chelumni, the fish possessed a body form almost unchanged from fossil relatives known from ancient rock. A second species, Latimeria menadoensis, was later identified near Indonesia in 1997. Within their paired lobed fins lies the same skeletal arrangement that later evolved into the limbs of tetrapods. In a direct anatomical sense, the movements of human arms and legs still carry the structural memory of those ancient fins. Along shorelines, horseshoe crabs continued another lineage that reached back toward the eurypterids. Only 4 living species remain, yet their general body plan has persisted for roughly 450 million years. They still gather along beaches to spawn in dense seasonal events, much as their ancestors likely did before vertebrates developed jaws. Their survival illustrates how some biological strategies require little alteration once they achieve durable ecological balance. Even more ancient in appearance are the hagfish, jawless vertebrates directly related to the agnathan fishes that drifted through Silurian and Ordovician waters. They remain scavengers of the sea floor, feeding on carrion in dark marine environments where competition is lower and stability greater. Their most remarkable adaptation is defensive slime composed of microscopic protein threads thinner than human hair. When released into seawater, these threads expand to roughly 10,000 times their original volume, forming one of the most unusual biological materials known to science. Across all 5 Paleozoic extinction events, a pattern emerges with remarkable consistency. Generalists outlast specialists, smaller animals outlast giants. Deep water species survive more reliably than shallow water species. Flexible diets endure where narrow ecological dependence collapses. The ancient ocean rewarded innovation during times of abundance, but during catastrophe it favored resilience above all else. Far below the reach of weather, beneath the shifting brightness of the surface ocean, the deep sea continues in a state that would feel strangely familiar to many of the animals that crossed the Paleozoic world. The modern abyss is not a preserved fossil, nor a frozen museum of ancient life, yet in specific biological and ecological ways, it remains the closest living analog to the oceans that existed before reefs of coral fish and marine mammals transformed shallow water into the ecosystems recognized today. Down there, darkness dominates completely. Pressure shapes anatomy at every scale, and survival depends on strategies that first emerged hundreds of millions of years ago. Below roughly 200 meters, sunlight fades into permanent night. Temperatures across most of the global deep ocean remain between 2 and 4 degrees Celsius, almost unchanged across immense distances. Pressure rises relentlessly with depth, increasing by approximately 1 atmosphere for every 10 meters of descent. At 1,000 meters, an animal exists beneath a weight difficult to imagine from the surface world, yet entire ecosystems persist within it calmly. Their bodies adapted to compression so completely that the environment itself becomes ordinary. The modern nautilus still drifts through this darkness, carrying one of the oldest body plans on Earth. Nautilus pompilius spends much of the day at depths approaching 700 meters before rising toward shallower water at night to feed. The mechanism guiding these migrations would have been recognizable in Ordovician seas nearly 470 million years ago. Gas-filled chambers within the shell regulate buoyancy through the siphuncle, allowing slow vertical movement through the water column with remarkable precision. The ancient orthocones that once hovered like living spears above trilobite fields operated according to the same principle. The shell coils changed, the diversity collapsed, entire oceans vanished, yet the fundamental strategy endured. Across the sediment plains of the deep sea floor, giant isopods continue another echo of the Paleozoic. Bathynomus giganteus can reach lengths approaching 50 centimeters and inhabit depths ranging from 170 to more than 2,000 meters. Their segmented armored bodies resemble enlarged relics of earlier arthropod worlds, and when threatened, they curl into defensive spheres, almost exactly as trilobites once enrolled themselves against Cambrian and Ordovician predators. They move slowly across the mud, searching for carcasses descending from above, surviving on scarcity with extraordinary patience. The deep-sea food web itself resembles older marine systems in important ways. Most energy arrives not through local photosynthesis, but through marine snow, the endless downward drift of organic particles from sunlit waters far overhead. Dead plankton, microscopic waste, fragments of tissue, and dissolving biological debris settle gradually toward the abyss like pale dust through black water. Detritivores and scavengers dominate much of this environment, recalling earlier seafloor ecosystems that existed before large, visually guided predators transformed marine life into an escalating arms race. Light also returned to the ocean in a different form. Approximately 76% of deep-sea animal species produce bioluminescence, generating flashes, pulses, and cold living glows through biochemical reactions within their bodies. Some use the light to attract prey, others to confuse predators, others to communicate across darkness that no sunlight can penetrate. The evolutionary roots of these systems may reach deep into ancient predator-prey conflicts where detection and deception shaped survival long before vertebrates ruled the sea. Many deep-water invertebrates also display a recurring tendency toward enormous size. Giant squid may exceed 13 meters in length, colossal squid possibly heavier still, while giant amphipods and giant isopods dwarf their shallow water relatives. In environments with fewer predators, slower metabolisms, and sparse but unpredictable food supplies, large body size can become advantageous once again, echoing the same evolutionary pressures that repeatedly produced oversized forms in ancient oceans. Across the abyssal floor, fine sediment continues settling grain by grain through spans of time almost beyond comprehension. Some deep-sea cores contain traces from the Cretaceous, the Jurassic, and even fragments of Paleozoic microfossils buried far below modern mud. The deepest ocean floor is not only a landscape, it is a layered archive of vanished worlds, where the bottom of the sea becomes indistinguishable from the bottom of time itself. Long before a fossil reaches a museum drawer or appears beneath the light of a laboratory microscope, an almost impossible chain of accidents must first occur. The ocean floor receives countless bodies every day, yet nearly all vanish completely. Flesh softens, scavengers feed, bacteria dissolve tissue into surrounding water, and currents scatter the remains until nothing recognizable survives. The ancient animals crossing this documentary exist in stone only because a tiny fraction escaped that ordinary ending. Their preservation is so statistically unlikely that every complete fossil can feel less like a discovery and more like an interruption in the normal disappearance of life. The science that studies this process is called taphonomy, the long transition from living organism to fossil. For preservation to occur, an animal typically must die in an environment low in oxygen where bacterial decomposition slows dramatically. Rapid burial beneath fine sediment is equally important, shielding the body from scavengers and water movement before delicate structures collapse. Over immense spans of time, mineral-rich groundwater passes through the buried remains, gradually replacing organic molecules with stone while preserving their original shapes. The transformation may require thousands or even millions of years, and most organisms never experience it at all. Paleontologists estimate that fossil evidence exists for less than 1% of all species that ever lived. The pre-fish oceans were therefore almost certainly more diverse than any reconstruction can fully capture. Every trilobite, eurypterid, placoderm, or anomalocarid known today represents not the average ancient organism, but one fortunate enough to die under extraordinarily specific conditions. Entire ecosystems may have existed and vanished without leaving a single recognizable trace. The creatures that entered the geological record are the survivors of survival itself. Some fossil deposits preserve far more than bone or shell. The Burgess Shale remains among the most extraordinary examples ever discovered. There, Cambrian organisms slid from a submarine escarpment into an oxygen-starved basin where decomposition nearly stopped. Their soft tissues became replaced by clay minerals with astonishing fidelity. Digestive tracts, muscle fibers, neural tissue, eye structures, and even the contents of intestines remained visible across more than 500 million years. The resulting fossils transformed understanding of early animal life because they preserved anatomy that normally disappears long before fossilization begins. Modern technology has deepened that understanding even further. Synchrotron X-ray tomography allows researchers to create detailed three-dimensional internal maps of fossils without cutting them apart. Computed tomography scanning reveals structures hidden inside solid rock. Electron microscopy can identify microscopic biological remnants, including melanosomes, pigment-containing organelles, whose shapes allow scientists to reconstruct coloration patterns in animals dead for hundreds of millions of years. Quantitative biomechanical modeling now tests fossil anatomy using the same mathematical frameworks employed in aerospace engineering and robotics. The compound eyes of Anomalocaris were analyzed through optical modeling software originally developed for modern camera systems. Researchers reconstructed the geometry of more than 16,000 lenses and calculated visual acuity directly from fossil structure. The findings, published in Nature during 2011, demonstrated that Cambrian predators possessed image-forming vision far more sophisticated than previously imagined. Dunkleosteus received similarly modern treatment. Finite element analysis, a technique used to evaluate stress in aircraft components and architectural systems, was applied to the fossilized geometry of its jaws to estimate bite force and structural performance during feeding. Behind these discoveries stand generations of researchers who devoted entire careers to reading stone patiently enough for the ancient ocean to answer back. Charles Walcott uncovered the Burgess Shale during 1909. Harry Whittington returned decades later and reinterpreted its impossible anatomy. Simon Conway Morris and Stephen Jay Gould transformed Cambrian paleontology into one of science's defining debates about evolution and contingency. Philip Janvier reconstructed early vertebrate history. Jakob Vinther revealed fossil coloration through microscopic chemistry. John Patterson helped reconstruct the visual systems of Cambrian predators from lens geometry preserved in shale. These animals are not inventions assembled from imagination alone. They are measured, scanned, modeled, chemically analyzed, and compared against the physics governing living organisms today. The stone does not speak quickly, and it rarely speaks clearly at first. Yet across enough time, enough patience, and enough careful observation, the ancient ocean continues to reveal itself layer by layer. Somewhere beneath every fossil in this story, beneath every extinction boundary and vanished reef, one number has remained quietly present the entire time: 500 million years. The phrase is easy to pronounce, but the scale behind it does not fit naturally inside the human mind. It slips away almost immediately, flattening into abstraction long before intuition can hold it properly. Human perception evolved for seasons, lifetimes, migrations, storms, and memory carried between generations. Deep time exists far beyond the range our instincts were designed to navigate. Most human intuition measures time through individual lives lasting perhaps 70 or 80 years. Generational memory extends only a little farther, perhaps 3 or 4 overlapping lifetimes, enough for stories told by grandparents to grandchildren. Recorded history reaches back approximately 5,500 years to the first Sumerian writing systems, while organized agriculture stretches perhaps 10,000 years into the past. Entire civilizations rise and disappear inside intervals that geology barely registers at all. Against this scale, 500 million years becomes almost impossible to visualize directly. It is 100,000 times longer than all recorded human history combined. The distance between Anomalocaris and Dunkleosteus alone spans roughly 145 million years. That single interval exceeds the entire stretch separating the first dinosaurs from the present day. Tyrannosaurus lived closer in time to modern humans than it did to Stegosaurus, yet even that enormous span occupies only a fraction of the temporal landscape explored throughout this documentary. The oceans crossed by trilobites, eurypterids, orthocones, placoderms, and early sharks were separated from one another by expanses of time so large that continents themselves drifted into unrecognizable positions between them. Every empire, every war, every invention, every language, every city ever built by human beings occupies only the thinnest surface layer atop this deeper chronology. The pyramids, the Roman Empire, the Industrial Revolution, the digital age, all compress into a geological instant too brief to form a visible layer in many sedimentary deposits. Most of Earth's history unfolded long before any creature existed capable of describing it. The Paleozoic oceans thundered with ecological conflict for hundreds of millions of years in complete silence, observed by no witness who could leave behind words. Paleontologists who spend decades working with these numbers often describe a particular mental sensation that develops gradually over time. At first comes disorientation, a kind of cognitive vertigo produced by scales too large for ordinary comparison. Eventually, that vertigo softens into something quieter. The present moment begins to feel exceptionally recent, almost fragile in its brevity. Human history no longer appears ancient but immediate, suspended at the farthest edge of an incomprehensibly long continuum. The worlds inhabited by Anomalocaris, Cambrian, Dunkleosteus, and the giant eurypterids were not primitive rehearsals for modern ecosystems. They were complete worlds unto themselves, internally stable and ecologically sophisticated, persisting across spans of time that dwarf the entire existence of mammals. Their reefs, predators, migrations, and extinctions were not moving toward a predetermined outcome. The Cambrian Ocean was not trying to become the Devonian, and the Devonian was not anticipating the modern Atlantic or Pacific. Each age existed fully within its own conditions, shaped by chance, adaptation, and survival, without direction or intention. What happened, quietly and improbably, was that a lineage of small, jawless vertebrates survived enough environmental collapses to continue forward. The end Ordovician extinction might easily have erased them. The late Devonian crises might have ended their branch permanently. Dozens of smaller extinction pulses scattered across the Paleozoic could have altered the outcome completely. Had even one of those events unfolded slightly differently, the chain leading from primitive vertebrates to mammals, primates, and eventually human beings might never have continued. In that alternate Earth, the oceans would still have existed. Continents would still drift. Reefs would still rise and collapse beneath changing climates. Sharks or cephalopods or entirely different lineages might dominate the sea. The sun would still cross above the planet each day, but no documentaries would ever be written about those vanished oceans because no one would exist to remember them at all. Inside the human body, ancient oceans continue their motion silently. The pulse of balance in the inner ear, the involuntary tightening of muscles after a sudden sound, the ability of the eyes to focus upon distant movement, even the structure of the jaw-shaping spoken words, all carry traces of evolutionary pressures first imposed hundreds of millions of years ago. The monsters that crossed Cambrian and Silurian seas are gone as living organisms, yet the problems they created remain embedded within vertebrate biology. Every modern nervous system still carries solutions forged during those distant ecological wars. Long before vertebrates became dominant predators, survival depended increasingly upon vision. Arthropod hunters, such as Anomalocaris and later eurypterids, transformed the ocean into an environment where detecting movement at distance could determine whether an animal continued living at all. Vertebrates evolved a different answer to this challenge than arthropods did. Instead of compound eyes composed of thousands of separate lenses, early vertebrates developed the camera eye, a single aperture system using a lens to focus light onto a retina. This arrangement allowed detailed depth perception and improved sensitivity in dim conditions. The human eye still follows this same architecture. The muscles adjusting focus, the retina converting light into electrical signals, the optic nerve carrying information into the brain, all belong to a visual lineage shaped in waters where failing to detect motion quickly enough often ended in death. The vertebrate fear response also carries roots extending back into those early oceans. Sudden sensory input still triggers an immediate neurological cascade through the body before conscious thought fully forms. Muscles tense, heart rate shifts, attention narrows, and movement prepares itself almost instantly. In modern vertebrates, this process involves deep brain structures, including the amygdala. Yet, the foundations of these rapid threat detection systems emerged far earlier in primitive nervous systems, responding to predators that attacked with speed and little warning. The reflexive startle response experienced today belongs to an inheritance refined under the pressure of animals like Anomalocaris, Dunkleosteus, and giant eurypterids moving through ancient water. The human jaw carries perhaps the clearest physical connection to this history. Early vertebrate jaws evolved gradually from modified gill arch structures, transforming breathing supports into articulated feeding mechanisms, capable of grasping and processing increasingly difficult prey. Every human bite still depends upon that innovation. Speech depends upon it as well. The movements shaping language, conversation, singing, and breath all rely upon anatomical structures whose original evolutionary function involved consuming armored organisms in Paleozoic seas. Even the sense of balance within the skull reflects the demands of ancient aquatic survival. The semicircular canals of the inner ear detect acceleration and orientation through fluid movement inside delicate chambers. In early vertebrates, these systems provided critical information about rapid motion through water, helping animals respond to currents, pursue prey, or detect approaching predators before direct contact occurred. The modern sensation of tilting the head, stumbling briefly, or recovering equilibrium while walking represents a deeply ancient sensory system refined in environments where spatial awareness could determine survival within seconds. The vertebral column itself emerged as a solution to limitations imposed by exoskeletons. Arthropods achieved protection through external armor, but molting created intervals of extreme vulnerability while the new exoskeleton hardened. Vertebrates followed a different path. An internal skeleton allowed continuous growth without repeated defenseless phases. The spine provided structural support for larger body sizes while preserving mobility and reducing the risks associated with shedding an external shell. Every vertebrate body today, from fish to birds to mammals, still depends upon that ancient structural innovation. The immune system also bears the imprint of these vanished seas. Early vertebrates evolved increasingly sophisticated adaptive immunity within environments dense with microbial life and frequent physical injury from predator attacks. The ability to recognize specific pathogens and retain biological memory of previous infections became enormously advantageous in ecosystems where wounds were common and bacteria abundant. Modern immune responses still operate through mechanisms shaped during those long prehistoric struggles between injury, infection, and survival. None of this exists merely as metaphor or poetic resemblance. The ancient oceans described throughout this documentary survive materially within the biology of every vertebrate alive today. Nervous systems, sensory organs, skeletal structures, reflex pathways, and immune defenses all preserve solutions developed during those early evolutionary conflicts. The monsters vanished, yet their pressures endured, written permanently into flesh across hundreds of millions of years. In a precise biological sense, the ancient ocean never truly disappeared. It continued forward inside the bodies of its survivors, and eventually inside us. Far beneath shipping lanes, coastlines, satellites, and human borders, the ocean continues moving through darkness exactly as it did before forests existed on land. Currents still descend into abyssal plains older than mountains now standing on continents. Tiny organisms still drift downward through black water in a constant snowfall of organic matter. Predators still rise from depth under cover of night. The actors have changed many times across geological history, yet the stage itself has never closed. The ocean described throughout this documentary is not lost in the way vanished cities are lost. It still exists around us, continuous and alive. For approximately 3,800 million years, life has persisted within Earth's oceans without interruption. Extinction events erased dominant lineages, altered chemistry, collapsed ecosystems, and rearranged the architecture of marine food webs, yet no extinction ever emptied the sea completely. During the end Ordovician crisis, life contracted and endured. During the late Devonian collapse, reefs vanished, and predator dynasties disappeared, yet the ocean remained inhabited. Even during the end Permian catastrophe, when approximately 96% of marine species vanished, survivors still moved through the remaining water. There has never been a silent ocean. Not once. The water itself carries continuity difficult for the human mind to hold clearly. Molecules within the modern sea cycle continuously through evaporation, rainfall, glaciers, rivers, groundwater, clouds, and ice before returning again to the ocean basin. Some fraction of the water touching coastlines tonight almost certainly circulated through Cambrian tides more than 500 million years ago. Some portion of the Pacific, moving now through deep trenches, may once have drifted above trilobite beds or passed through Ordovician reefs crowded with crinoids and nautiloids. The ocean changes constantly, yet it also persists materially across spans of time so immense they begin to feel motionless. Its chemistry has shifted continuously throughout that history. Cambrian and Ordovician seas contain different oxygen distributions and higher calcium carbonate saturation, conditions that encourage the explosive diversification of shells, armor, and mineralized skeletons during the early Paleozoic. Surface waters were often warmer, and many marine environments remained low in oxygen compared with much of the modern ocean. Stratification patterns differed, currents differed, coastlines differed. Yet through all those transformations, the sea remained chemically compatible with life. Organisms adapted alongside the water itself, each evolutionary wave rewriting the balance between chemistry and biology. The ocean floor preserves much of this story patiently beneath accumulating sediment. Layer upon layer settles through darkness every year, trapping shells, microorganisms, chemical signatures, and fragments of vanished ecosystems. Some sediments now resting beneath abyssal plains began forming during the age of dinosaurs. Others preserve microscopic traces reaching deeper into geological time. Fossils described throughout this documentary remain embedded within stone-below deserts, mountain ranges, cliffs, and seabeds, while additional remains continue entering the sediment record even tonight. Somewhere in darkness, an organism dies, settles quietly through the water column, and begins the long transition towards stone. In the western Pacific, near regions surrounding Philippines, Fiji, and Palau, living nautiluses continue their slow vertical migrations through deep water. During daylight hours, they descend hundreds of meters into darkness, rising again at night to feed along reef slopes. Their buoyancy-controlled shells still regulate movement through chambers filled gradually with gas and liquid, preserving an ancient body plan that first flourished when orthocone cephalopods drifted through Ordovician seas. The lineage diminished almost beyond recognition in diversity, yet the strategy endured. Far deeper still, hydrothermal vent systems discovered in 1977 sustain ecosystems independent of sunlight entirely. Chemosynthetic bacteria convert mineral-rich vent chemistry into biological energy, supporting tube worms, crustaceans, mollusks, and microbial communities isolated within stable deep-sea conditions. Some researchers suspect these environments preserve echoes of extremely ancient biological strategies, maintained in darkness for spans of time difficult to comprehend fully. Tonight's ocean and the Cambrian Ocean are separated by approximately 538 million years of uninterrupted change. Yet they remain the same planetary body of water, the same circulating system, the same continuous story, only the handwriting changed. Long before language emerged, before memory could be written into symbols or preserved in stone inscriptions, living creatures were already navigating the world through sensation. Light touched primitive eyes. Water pressure bent sensory hairs. Chemical traces drifted through seawater and were interpreted by nervous systems built from living tissue. Hunger altered behavior. Injury changed movement. Predators pursued prey through decisions, unfolding moment by moment inside minds that vanished hundreds of millions of years ago without leaving testimony. The fossils preserve bodies, not experience, yet the question remains suspended beneath the entire history of the ancient ocean. What did it mean, in however faint or alien a form, for these creatures to be alive? The fossil record cannot directly answer that question. Stone preserves anatomy, traces of behavior, environmental context, and sometimes even microscopic structures within tissue. But subjective experience does not fossilize. No trilobite left a description of darkness. No Anomalocaris recorded the sensation of movement through water. Yet, neuroscience and behavioral biology allow certain careful inferences. Nervous systems obey physical principles continuous across evolutionary history. Organisms with complex sensory structures and centralized neural processing almost certainly experienced the world in ways more sophisticated than simple mechanical reaction. Fossilized neural impressions recovered from anomalocarid specimens reveal brains strongly organized around vision. Large optic lobes correspond closely to the enormous compound eyes that dominated the front of the animal. This was not merely a body responding blindly to brightness or shadow. It was a predator processing spatial information, tracking movement, adjusting orientation, and coordinating pursuit within a visually structured environment. The ocean of the Cambrian was becoming a place interpreted through sight, and Anomalocaris belonged to the first wave of animals equipped to experience that transformation neurologically. The eurypterids carry another thread of evidence forward through evolutionary continuity. As chelicerates, they belong to the same broad lineage as modern spiders and scorpions, animals whose behavior today reveals patterns extending beyond automatic reflex. Experiments with spiders have documented anticipatory posture changes before attack. Environmental preferences maintained across repeated exposure, and altered responses after injury that suggest some form of internal state modulation. None of this proves consciousness in a human sense, yet it complicates the older idea that invertebrates operate as unfeeling machines. Their behavior contains flexibility, adjustment, and persistence shaped by ongoing interaction with the environment. In 2012, a group of prominent neuroscientists signed what became known as the Cambridge Declaration on Consciousness, stating that non-human animals possess neurological substrates associated with conscious states. The declaration extended beyond mammals and birds to include animals with sufficiently complex nervous systems, including some invertebrates. It did not claim that consciousness is identical across species. Rather, it acknowledged that subjective experience likely exists along a spectrum broader than human intuition once allowed. Certain statements can therefore be made carefully and precisely. Anomalocaris tracked prey through active visual pursuit. It altered movement based on prey behavior. Sometimes it succeeded, and sometimes it failed. In living organisms today, those patterns correlate with attention, information processing, and forms of learning. Whether that internal activity resembled anything recognizable to human awareness remains unknown, perhaps permanently unknowable. Still, the deeper question lingers quietly beneath the science. What was it like to move through a world where your eyes resolved details no other nearby creature could perceive clearly? What was it like to inhabit an ocean filled with drifting shadows while possessing the first nervous system sophisticated enough to transform those shadows into meaningful spatial reality. No fossil can answer. The question survives precisely because it cannot be resolved completely. And now another consciousness enters the story, one separated from Anomalocaris by more than 500 million years. A human mind sits in darkness, thinking about an animal long erased from the living earth, reconstructing its movements from stone fragments and preserved anatomy, imagining its existence with empathy directed backward across geological time. The ancient predators could not know they would one day be remembered. Yet they are remembered. Consciousness, at least in part, may be the ability to hold the existence of something absent and still allow it to matter. There is a habit in the way humans tell evolutionary history, a quiet instinct to divide the past into winners and losers. The surviving lineages become protagonists. The extinct become mistakes, rough drafts, abandoned experiments erased by something better, adapted to reality. Beneath many descriptions of the ancient ocean rests an unspoken narrative that the monsters described throughout this documentary failed, while fish succeeded, and that the modern world emerged because evolution steadily improved its designs toward the present moment. Yet, the fossil record does not describe progress in that way. It describes persistence, contingency, interruption, recovery, and immense stretches of time during which entirely different worlds functioned perfectly well without us. Anomalocaris occupied the apex predator role in Cambrian seas for approximately 40 million years. That span alone exceeds human intuition. The genus Homo has existed for perhaps 2 or 3 million years. Anatomically modern humans have existed for roughly 300,000 years, a geological instant so brief it nearly disappears against Paleozoic timescales. By duration alone, Anomalocaridids were astonishingly successful organisms. They spread across ancient oceans, diversified into multiple forms, transformed marine ecosystems through predation, pressure, and maintained dominance for a period vastly longer than human civilization has existed. The same pattern extends across the other dynasties that followed. Cambrian and related orthocone nautiloids ruled portions of the Ordovician Ocean for tens of millions of years, drifting through reef systems and open water as stabilized ambush predators of extraordinary scale. Eurypterids survived across more than 200 million years, enduring environmental upheavals that erased countless competing groups. Trilobites persisted for approximately 270 million years, diversifying into more than 20,000 described species while occupying nearly every marine habitat available to arthropods. These are not the histories of failed creatures. They are among the longest and most successful biological stories Earth has ever produced. Extinction does not retroactively erase achievement. A lineage that thrives for 40 million years before disappearing remains a lineage that thrived for 40 million years. Geological duration changes the emotional meaning of success entirely. Human cultures often measure value through permanence, yet nothing biological remains permanent. Even survival itself is temporary when viewed across deep time. The trilobites did not fail because they vanished. They succeeded for longer than mammals have existed. The fish that eventually inherited marine dominance did not conquer the previous rulers through some inevitable superiority. In many cases, they survived because they occupied ecological positions less exposed to extinction pressure. Small body size, flexible diets, wide environmental tolerance, rapid reproduction, and habitation of marginal environments repeatedly increased survival odds during planetary crises. During the end Permian extinction, approximately 96% of marine species disappeared. No organism overcame such conditions through strength alone. Survival depended on geography, metabolism, food availability, oxygen access, reproductive timing, and immense ecological chance distributed unevenly across the planet. Enough fish lineages happened to persist in enough surviving environments that vertebrates later expanded into emptied ecosystems during recovery. Had those extinction boundaries shifted even slightly in severity or timing, entirely different lineages might have inherited the open niches of the post-Paleozoic ocean, a world dominated by cephalopods, arthropods, or something stranger remains biologically imaginable within the logic of evolutionary history. This changes the meaning of the ocean visible tonight. The fish-dominated marine world familiar to human eyes is not the final form of ocean evolution, nor the intended destination toward which ancient ecosystems struggled. It is one temporary arrangement produced by a specific sequence of catastrophes and recoveries unfolding across hundreds of millions of years. Different extinction patterns would have written different oceans. Different survivors would have carried different body plans forward into the future. And beneath that realization rests something unexpectedly gentle. The ancient monsters were not building toward us, failing to become modern, or waiting to be replaced. They were complete worlds unto themselves, living fully inside their own time, under their own skies, within oceans that belonged entirely to them while they lasted. At some point during a story this large, the ancient ocean stops feeling distant. The names become unfamiliar, less because they are alien, and more because they are old, beyond ordinary emotional scale. Creatures drift through darkness, rise toward prey, vanish into extinction, and leave behind fragments of shell or impressions in stone. Yet something about their existence presses strangely close to the present moment. A listener lying awake in darkness can feel the weight of a world erased hundreds of millions of years ago, even while knowing intellectually that none of those animals ever saw a human sky. The question beneath the final movement of this story is not only what happened in the Paleozoic ocean, it is why that history reaches so deeply into the modern mind at all. Part of the answer rests in scale. Human attention is usually trapped within immediate distances and brief durations. A day feels large while it is happening. A year feels long. Entire lifetimes can appear enormous from inside them. Then deep time arrives and quietly rearranges proportion. 500 million years is so vast that ordinary worries begin to lose their apparent permanence. The mind struggles to hold the scale directly, and in that struggle, something loosens. Personal anxieties shrink toward their true geological dimensions, which are extraordinarily small. The ancient ocean becomes a kind of mirror in reverse, reflecting not human importance, but human briefness. Another part of the answer is continuity. Learning that life did not begin with humanity, or mammals, or vertebrates, but extends backward through almost unimaginable spans of biological history, alters the feeling of isolation many people carry without realizing it. The story did not start with us. It began long before forests, before dinosaurs, before fish possessed jaws, before eyes evolved the capacity to form sharp images. The living world surrounding humanity tonight is part of a chain extending continuously into Cambrian seas more than 500 million years ago. To understand that you are not standing at the beginning of the story, but somewhere in the middle of it, changes the emotional texture of existence itself. You belong to something ancient, Deep time also changes the meaning of loss. In ordinary human experience, endings feel absolute. Species disappear, individuals die, entire ecosystems collapse. Yet across geological history, destruction repeatedly becomes the condition from which new worlds emerge. The end Ordovician extinction eliminated the giant orthocone predators and transformed marine ecosystems profoundly. Yet those empty ecological spaces later allowed entirely different vertebrate lineages to expand. The Devonian collapse erased Dunkleosteus and the placoderms, opening pathways through which sharks and ray-finned fish diversified across the oceans. Every extinction described throughout this documentary carried catastrophe within it, yet each also reshaped the possibilities available to the survivors that followed. That continuity remains physically present inside living organisms today. The monsters of the Paleozoic are not preserved only in museums or fossils embedded in cliffs. Their influence survives biologically, written into anatomy, reflexes, and nervous systems inherited across evolutionary time. The vertebrate eye emerged under predation pressure created partly by ancient arthropod hunters. The jaw developed from gill structures within oceans already shaped by armored prey and pursuit predators. The spine, balance systems, and rapid threat detection responses operating in modern vertebrates all carry traces of evolutionary problems first encountered in seas filled with creatures now long extinct. Even the act of listening to this documentary depends upon ancient adaptations shaped in those vanished worlds. The ears processing sound, the eyes moving across darkness, the nervous system orienting attention toward patterns and movement, all emerged from biological histories extending backward into the Paleozoic ocean. The ancient predators helped sculpt the sensory architecture through which modern humans perceive reality itself. This is what deep time quietly reveals about endings. Very little disappears completely. Biological forms vanish, yet their consequences remain embedded within the organisms that inherit the altered world left behind. The ancient ocean did not truly end. It transformed, transmitted itself forward, and continued speaking through different bodies. The monsters remain present, not as ghosts, but as living inheritance carried silently through every creature alive tonight. Across the Pacific tonight, below waves reflecting moonlight no ancient trilobite ever saw, a nautilus is ascending slowly through dark water, several hundred meters beneath the surface. Pressure still surrounds its chambered shell with crushing force, yet the animal rises calmly by regulating buoyancy, the same way its ancestors once drifted through Ordovician seas. Near midnight, it will reach the outer reef slopes, extend more than 90 soft tentacles into the current, search for food among rocks and coral, and then descend again before morning light returns to the water above. It does not carry memory of the ancient ocean. It does not know it belongs to one of the oldest surviving lineages on Earth. It is simply continuing a rhythm that has persisted for hundreds of millions of years. Along shorelines tonight, horseshoe crabs are also moving through an older rhythm. On beaches near Delaware, along coasts bordering the Yucatan Peninsula, and across stretches of shoreline throughout Southeast Asia, they emerge beneath spring tides and moonlit water to lay eggs in wet sand before turning back toward the sea. Their bodies still resemble forms that crawled across Paleozoic seafloors long before vertebrates became dominant predators. Their distant relatives once shared marine ecosystems with eurypterids and trilobites beneath Silurian skies now erased entirely from the planet. Yet the behavior remains. The ocean taught it to their lineage long ago, and the lesson continues repeating quietly tonight. Far deeper, Beyond continental shelves and descending slopes, the Hadal trenches remain almost untouched by surface weather or human sound. In the great trenches of the Pacific, including the Mariana Trench, the Tonga Trench, and the Philippine Trench, giant amphipods and deep-sea isopods move slowly across sediment, accumulating grain by grain through immense spans of time. Darkness there is complete. Pressure compresses every surface. Very little disturbs the sea floor. The animals living within those depths experience an environment closer in tempo to geological time than to human time. Entire civilizations rise and vanish, while abyssal sediment settles only a few centimeters thicker. Elsewhere tonight, beneath laboratory lights instead of moonlight, paleontologists continue opening fragments of ancient worlds. In research collections from Bristol to Yunnan province, and inside drawers preserved within institutions such as the Smithsonian Institution, pieces of stone still contain animals no human being has formally described yet. Somewhere a fossil rests inside shale, preserving details of soft anatomy impossible to see from the surface. Somewhere an eye lens, a feeding appendage, or the trace of a nervous system waits beneath rock for imaging technology capable of revealing it clearly. Perhaps tomorrow, or next year, or decades from now, another ancient creature will receive a scientific name, and the history carried through this documentary will become slightly less incomplete. The modern ocean is not identical to the seas that carried Anomalocaris or Dunkleosteus. The chemistry differs. The continents shifted. Entire dynasties vanished and were replaced by others. Fish dominate where arthropods once held supremacy. Mammals now enter waters that once belonged only to gills and shells. Yet continuity remains beneath the transformation. The same planetary ocean still circulates through darkness. The same pressure still builds in deep trenches untouched by sunlight. The same cold persists in abyssal plains where ancient sediment continues falling silently through black water. And tonight, whatever thoughts or worries arrived beside you into darkness belong to the brief scale of a human life, real and meaningful within that scale. Yet beyond those immediate horizons, the ocean continues moving through a story older than forests, older than vertebrates, older than complex life itself. For approximately 3,800,000,000 years, it has endured extinctions, recoveries, and transformations beyond ordinary comprehension, and still it remains. The ocean is old. It has watched entire worlds appear and disappear beneath changing stars. Long before human eyes opened, it was already here, deep and moving in darkness. Long after tonight passes into memory, it will remain, carrying ancient life quietly through the water the way it always has.